Hello, everyone, and welcome to today's webinar slash training. We are very, very grateful to have you join us today. We have a packed, exciting session set up for you. We are very excited and for you joining us today. This webinar and training is part of the activities that we are doing in the run up to the World Energy Day conference taking place in this October, and for the first time will take place at the Pearl of Africa in Kampala, Uganda. Very excited to see in our attendance Ugandans as well. So very, very warm welcome to everyone. Today's topic is on technology updates in energy efficiency. And before I unpack the topic and the great lineup of speakers that we have, I would like to just quickly mention some housekeeping rules that we ask you adhere to. And okay, great. And we love an engaging audience. However, we do love order. So we kindly ask that you mute your mic throughout the session unless called upon. And if you have questions, we do have pockets of question and answer where you'll be able to ask your question to the speakers, to the moderators. Additionally, the chat option is open. Feel free to utilize the chat. Post your questions. We do have a chat master who will be able to note out your questions. You can also use the raise hand feature on the reaction on the down below, and we will be able to note you out. And looking forward to a great session. In fact, let us just do a warm up and use the chat now to shout out where you're joining us from. I'm in Nairobi, Kenya. It's a bit chilly, but very excited to see where we are all joining in from. Feel free to use to utilize the chat now to shout out where you're joining us from. And as we do that, I can now move on to why we are here. As I've mentioned, this is part of the World Energy Day activities running up to October. And World Energy Day 2021 is an exciting partnership with UNREA. This is an umbrella organization in Uganda that is involved in everything renewable, everything energy efficiency, and we are so excited to be in partnership with them. Additionally, we also have IEPA, who are the certified and represent the international certification body AEE in sub-Saharan Africa, where they are able to provide certified courses, and they have partnered with us in this training session today. And just about now, we see Kampala, Uganda. It's great to see everyone. We have Machakos County. Welcome. Greetings from Naivasha. I hope the Safari Rally is going on well. Excited to see where everyone is joining in from. Welcome all. And as we are in the spirit of knowing where we are from, I would just like to run a quick poll to see who we have in the audience before we move on to our first speaker. I'll now request Ruth or Karen to share the poll. There we go. Please feel free to mention or just tap the profession that most likely describes you, and then we will share the results in a few. A little more. We can close in about 2 minutes. Let's go ahead for those who haven't yet selected a sector. Hello, Malkia from Kampala. And Alfred from Gilgil, thank you. Thank you for joining us today. Karen, I don't know if we are able to share the results. There we have it. It seems we are mostly from the energy industry with 87%. We have finance at 3%, government at 3%. For those who are in the other section, feel free to explain where you're from in the chat. Thank you very much for joining us today. You are in the right place. It's a 2-day session. We have 4 speakers today. We have 4 other speakers tomorrow. So today, our first speaker will talk on a topic that has been considered to be in the top 5 trends to look out for in energy management. He is an electrical and electronics engineer by training, a software developer by passion, and an energy engineer in practice. He is going to talk about a topic on real-time monitoring in energy management. His name is Martin Ochieng. Welcome, Martin. We are more than excited to hear from you today.
Okay, thank you very much, Liz. Thank you for that spirited introduction. Let me just dive right in one moment.
Great.
Yes, so thank you very much, Liz, for that spirited introduction. And as Liz has mentioned, I'm an energy engineer at Innovators. My name is Martin Ochieng, and I'm going to be talking about real-time energy monitoring and analytics. So without much further ado, let me dive right into the topic at hand today. Maybe the first question we need to ask ourselves is what exactly real-time energy monitoring is in the context. And on a little, maybe doing a bit of research, I was able to identify a couple of different definitions of what we're talking about regards to real-time monitoring. First is that this is the delivery of continuously updated information, streaming at 0 or low latency. Maybe another definition could look at it as the employment of applications and tools that track and record continuous snapshots of your network's overall performance. That's we're looking at real-time energy monitoring within the context of network analytics and security. But pulling it closer to maybe the subject at hand today is that we can look at real-time monitoring in the context of energy management as the continuous collection of data from processes and utilities to understand exactly how, when, and why we use energy the way we do. And as you can see from all these definitions, the main key item that we're looking into is data. Basically being able to gather this data and be able to store it somewhere and analyze it is actually the process, maybe the point behind real-time energy monitoring, especially with regards to energy management in this particular context. Now, trying to look at that, maybe that view of data as one of the most important things that we're looking at with regards to real-time energy monitoring, it's important to identify exactly what the goal of real-time energy monitoring and analytics is. And I like to look at the goal of real-time monitoring as maybe very, very closely related to the goals for big data. And as you can see, maybe a quote from Carly Fiorina, an ex-CEO from Hewlett Packard, that's HP. She once said that the goal is to turn data into information and information into insight. I like to take that as maybe co-opt that a bit as one of the maybe one of the goals of or rather one of the main goals of real-time energy monitoring. The idea is to collect data from the ground, turn that data into information, and turn that information into insight we can actually use to help us better manage our energy. But I think it's good to actually identify exactly what is meant by this particular goal here, turning data into information and information into insight. And we're going to look at 2 examples of companies around the world that are maybe taking advantage of big data and turning that data into insight, information and information into insight to help them run their business, or rather to help them run their businesses. And I'm sure most of us are familiar with this particular company here, Netflix. Netflix itself is actually a streaming service, and it has a massive data repository of our viewing habits. It knows exactly what we like to watch, when we like to watch it, and how long we like to watch it, maybe to watch this particular content. And it usually uses that information to develop original content. Maybe just an example of maybe this particular action in practice, basically taking data into information and information into insight, is what Netflix did in 2015. I'm sure most of us are familiar with the actor Adam Sandler. So around 2015, he was getting a bit unpopular in the United States. However, Netflix still commissioned content with him in 2015. And the reason for this was that maybe data from viewing habits in Latin America showed that his previous works was significantly popular within that particular segment. And Netflix used that data to actually develop, rather to commission content with him to be able to take advantage of this particular market share that they had. Maybe the data that data had showed them, maybe they could actually take advantage of. So that's one example of a company taking that, maybe using data to actually help them make decisions moving forward. Just another example on maybe how data can be valuable in this particular context, rather taking data from information into that data into information into insight, is Google. Whenever we talk about data, or rather big data, most cases you can't have that conversation without involving Google, which has a large repository of data and actually has indexed a significant section of the internet. Yeah, so basically Google uses this particular data for marketing and of course product development. And we know several products go from Google, ranging from the Android, the operating system, Gmail, Google Drive, YouTube. Yeah, so Google uses their massive amount of data that they've collected to be able to develop these particular products and actually develop features for those particular products. But let's maybe pull it back a little bit closer to the subject, maybe to the subject matter today in energy. And I'm sure some of us are aware that Google is developing maybe several different artificial intelligence approaches. And one of these is called the DeepMind AI. And they've been able to use it to actually reduce energy consumption in their data centers by up to around 30%. The concept involves taking a large amount of data from sensors within the facility, that may be temperature sensors, electricity consumption sensors, maybe humidity sensors within those data centers, taking all that data and pushing into the DeepMind AI. And the DeepMind AI is able to analyze this particular data and convert that into information, and information into insight. Basically, from the data is able to collect, it can anticipate the data center needs and further move forward to actually optimize those maybe the energy consumption from those data center, maybe optimize the condition within those data centers to make it so that they consume maybe rather they are as efficient as possible with regards to the energy consumption. So those are some of the examples of other companies taking advantage of data and maybe putting it into practice to be able to maybe further their maybe their business activities. However, let's try to see how we can actually, maybe just a brief on how we can actually apply this into our case, or rather the subject matter today, which is energy management. Yeah, as you can see, this chart here indicates there are three specific layers with regards to maybe the ability to apply real-time energy management and analytics, and of course data, the use of data in this particular context. And the two most important layers are the hardware layer and the software layer, with the data logging analytics layer maybe right in between. The hardware layer involves the collection of data. Basically, in this case, we're talking about energy data. It may be electrical, diesel, and as you can see, we actually go a little bit further into collecting a little bit more than just energy data by collecting data from the items such as the water consumption, the temperature, production, and water view. The idea behind this is to be able to provide a way to actually make sense out of this data, to help us in the software layer to analyze this data, to understand exactly where we use energy, when we use it, and why we use it the way we do. Sitting at the center, there is the data logging and analytics layer. Its cruciality comes in drawing from the fact that energy data is actually quite a lot. Maybe in this particular field, the type of data collected with regards to energy is usually there's this particular word that this particular phrase that we use, time series data. The idea behind that is that the data is coming in as time moves by, meaning that the amount of data that you collect is significantly large, and the ability of you to actually analyze this data depends on your ability to actually collect the data and store it in a way and be able to call that data with the way you need. So that makes the data logging and analytics layer very, very crucial to provide help now to the software layer, which now involves now the human aspect, where we can have individual people looking at this particular information, and in some cases converting the information themselves into insight, or rather, and in some instances having the analytics layer itself convert it directly into insight. So this is basically a rundown of how we can approach the use of real-time energy monitoring and analytics now into maybe into the energy space. Basically now converting data into information into insight within the energy space. And there are several ways of doing this. Rather, there are several different approaches that different companies have been able to do this. As I mentioned, the two most important layers are the hardware layer and the software layer. For the hardware layer, there are so many different types of meters you can actually use to collect that particular data. There's the e-gauge, which is one of the main meters that our software uses. There's the AccuRev, there's the Watt Watchers, there's the Schneider Comex, various different ways of looking at how to get that particular data. And the meter that this particular image here shows one of the meters, which is the AccuRev meter. On the software side, there are several different softwares you can actually use to now maybe take advantage of this particular emerging technology. There's the EGOS Energy Management Platform, which is the one that I've been working on for the last 2 years. There's Safi Analytics, there's Vertex, there's Discema, various different players within the field, all with different maybe different advantages and different disadvantages here and there. But I'm not going to dig deep into each and every one of them. But I'm going to highlight the one that I've been working on a little bit more over the last few years. This is the EGOS Energy Management System, and its approach uses maybe on the hardware side, maybe it uses a couple of different hardware solutions. For instance, as you can see, the first one there, that's the Watt Watchers. The benefit of the Watt Watchers is that it goes a little bit further from just collecting energy data, and also go a little bit further into now helping you actually maybe take advantage of the aspect of control, being able to shut on and off a switch remotely. Then there's the e-gauge right here, which is one of the most powerful data collection tools that I've ever maybe interacted with. It can collect data from a range from energy to temperature to pulse inputs to analog inputs. Basically, the limits to what you can do with this particular meter is actually only limited by your imagination. And there's of course water data. Our system also collects data from water through a couple of different approaches there. And as you can see here, this is a sample dashboard showing exactly maybe what you can actually be able to access directly on the dashboard. And as you can see, you can modify this dashboard actually to add insights that you'd like to look at a glance in that particular context. So that's basically one of the ways that we approach. Maybe you can approach energy management, rather real-time energy monitoring and analytics. Basically, take advantage of data. That's the EGOS Energy Management Platform. Moving forward, I think it would be beneficial for us to understand exactly what the benefits of data and by extension real-time energy monitoring. Maybe what benefits you can accrue from this particular approaches here. And the first one is, of course, automation. As an energy engineer, I've worked with several different companies, and I've seen some companies maybe running programs where individual people have to go and take readings from a meter every single morning, which is prone to inaccuracies and inconsistencies. So that's one of the benefits of real-time monitoring. Real-time monitoring can actually be able to take that data in such a way that you don't have to actually make that data collection process manual. It helps you make informed decisions where you can actually use data from the ground to actually help inform your decisions, to make it so that the decisions that you make actually a little bit more accurate, a little bit more effective moving forward. It also helps you identify issues before they escalate. Basically, from one, as long as you're consistently collecting data, you can actually identify specific sections whenever maybe something happens that is maybe a bit far from the usual. Maybe real-time monitoring can actually help you maybe identify such issues. Can also help you find solutions to issues. Some of the solutions that we actually need with regards to energy management and real-time, basically energy management, can actually get from real-time monitoring. Basically, from understanding the data, we can actually figure out exactly how to make changes to that particular in that particular context. Great. So we can also help us get the results that you want, basically by continuously monitoring what's happening with regards to your energy consumption. You can actually identify specific instances where maybe your energy consumption is moving maybe towards where you don't want it to move, and actually perform course correction to be able to ensure that you can actually get the target that you're looking for. It also helps you get the best out of your resources, and also helps with planning. Basically, as long as you have enough data, you can actually be able to maybe plan on exactly how you're going to maybe operate, rather how you're going to maybe take advantage of your resources moving forward. Now that you looked at a rough example of benefits, I think it's important to also try to take some of these benefits to task and figure out exactly how these particular benefits actually apply with regards to maybe actual real life situations on the ground. And I'm going to take you through 3 case studies. The first one is for a compressed air. I'm sure some of us are familiar with the compressed air, or rather with compressed air compressed air systems within the industrial sector. And there are several different types of compressed air, but we're going to be focusing on one specific one, which is the load and unload compressor. So for one of our clients during an energy audit, our team was able to install a real-time energy monitor. And from the monitoring data, basically from the data that we're getting, we noticed something peculiar about the compressor. Basically, a normal compressed air, the load and load compressed air should be operating in this particular section here, within the ideal load cycling here. Basically, once it loads to the end, it should be able to unload and take a little bit longer on the unload cycle. But in this case, as you can see on the first section here, there was rapid cycling of that particular compressor, and we were able to identify maybe what the problem was. The problem was that the pressure band for that particular compressor's operation was a little bit narrow. It was between 6.5 and 7 bar, basically different of 0.5 bar, making it so that whenever this point it reaches 6.5 bar, the compressor loads up to this particular point here, where it reaches 7 bar. But once it does that, as it's unloading, it only unloads up to this particular point. At this point, it would have reached 6.5 bar, making it so that the energy consumption was a little bit higher than I expected. So we recommended that the team on the ground expand that pressure bar slightly and monitor the effects on maybe on the machines. And true to it, the company was able to take that up and try to modify that particular pressure bar. Yeah, as you can see, this initial section of data that is on the September section, this was when the pressure bar was a little bit wider, basically at 6.5 to 7 bar. And at the beginning of October here, we asked them to actually modify that particular action and maybe modify that particular pressure band and see maybe how it would affect the machines. And if it had any effect on the machines, they would return it to normal. And as you can see, over the whole month of October, the pressure bar remained between 6 bar and 7 bar, basically a difference, maybe a difference of 1 bar, and there was no notable effect on the machines. And as you can see, there's a significant energy consumption reduction there, as can be demonstrated by the EGOS, by the monthly report developed by the EGOS energy platform. And as you can see, for the compressor right down here, there's a reduction of around 4.8, close to 5% reduction in energy consumption for that particular utility, which amounted to around 20,000 Kenya shillings, roughly $200. So as you can see, we're able to, maybe through a real-time energy monitoring, we're able to save the company, convert data into insight, and be able to convert that insight now into actionable intelligence, which we're able to use to actually reduce the energy consumption for this particular compressor by around 4% and save the company around $200 without them having to invest anything. So that's not too shabby, if I may say so, within this particular context. Moving forward a little bit further, let's look at a second case study. This was for a hotel that we're working with, maybe we are constantly working with, to look at their energy consumption. And as you can see, the idea behind this particular approach was to actually help them. For this particular case study, I'm going to be bringing in now the human element in actually being able to get some of this insight. So our team was able to install a real-time monitor in the facility and identify the largest single consumer as the heat pump. I'm sure some of us are aware of what the heat pump actually is. And as you can see, moving forward into the next slide, the single largest energy consumer here was the heat pump, as can be confirmed here at around 17%. So our team was able to hold a meeting, basically an energy committee meeting. I'm sure some of us are aware of what an energy committee meeting, rather than an energy committee is. Basically a conglomeration of maybe representatives from different sections of our facility to be able to sit down and maybe analyze energy consumption patterns and try to identify how we can actually move forward with energy management. So we were able to hold a meeting with the energy committee and identify and we're able to identify specifically where the heat pump load was being wasted. And the following was the result. So this chart here is what we like to call a heat map. Basically, is a look into energy consumption per hour, maybe over a specific range. And as you can see, the darker shades, they indicate maybe a larger energy consumption. And as you can see, from around this point 2 p.m. to around 9 p.m. daily, there was a significant shift, or rather increase in energy consumption on the heat pump section. And through the energy committee meeting, we're able to identify the fact that this particular consumption was maybe appeared, might have been coincidentally, but appeared mostly during staff changeover. Basically, scenarios where maybe staff shifts, or maybe staff were changing shifts. And maybe drilling down a little bit further, we're able to identify that at this maybe on the staff changing rooms, the taps themselves, basically taps for washing the hands and a couple of other things, were mostly heated, drawing power from the heat pump. So from this, we're able to identify the fact that the heat pump is actually consume a little more than it should on the staff changing rooms, where the specifically on the taps, where it isn't really necessary to have this particular consumption on that particular section. So on further discussion with the team, we were able to identify the fact that there was a possibility of reducing energy consumption by maybe removing the hot water element from the hot water from the staff changing room taps. And this was the heat map for maybe the January trend heat map, as you can see. And as you can see on this, the latest heat map, this for last month. And as you can see, there's been a significant maybe change in how the patterns behave in that particular section. That means the consumption on that particular section, basically the staff, maybe the staff changing rooms has reduced significantly. And as you can see, drawing from data from energy consumption, drawing from January up to the end of around 14th June, as you can see, there's a significant reduction in energy consumption generally within that particular heat pump, maybe on the heat pump itself, which has made it so that the heat pump as at now isn't exactly now the highest consumer, but we've seen a significant reduction in energy consumption on the heat pump specifically, which is actually positive for this particular facility. So that indicates how we can actually use the real-time energy monitoring data in conjunction with the human element. Within this case, for instance, an energy committee, but reduce energy consumption. Maybe one last case study to be able to help us understand exactly how important real-time monitoring can be for us. And as you can see right now, we are still within in the middle of the pandemic, and it's important to actually see exactly what the pandemic meant, especially for last year with regards to energy consumption for different facilities. So I'm going to be looking at two facilities, one facility in Kenya, one facility in Uganda. The Kenyan facility is a hotel, and the Ugandan facility is a commercial building. So last year, COVID-19 restriction caused a significant drop in business. So let's try to see exactly how did this affect energy consumption, and maybe what insights can we draw from this. This is the Ugandan facility, and as you can see, from between January and I think towards the end of March, the energy consumption was almost as normal, but over the month of April towards maybe running through its end, I think this is the point where the COVID restriction really hit. You can see the significant reduction in energy consumption, but towards mid-May, the energy consumption returned to normal. Maybe one thing we can draw from this is that we can now actually understand the true base load for this particular facility and put it around 2,000 kilowatt hours. As you can see, these are scenarios where now most facilities actually, or rather most commercial buildings and hotels went completely down. And as you can see, it indicates that there's a significant base load, even in the case where this facility is not being used. So maybe there's an opportunity there to actually look at that particular consumption, identify maybe what you can actually reduce when you're not actually using the whole building. You can do the same for the Kenyan concept, which in this case is a hotel. And as you can see, there was a significant drop in energy consumption, I think towards the beginning of April through May, but the consumption came back up. And as you can see, because we're talking about a scenario of maybe close to total lockdown with hotels not actually doing business, this particular facility also has a significant daily base load, which can actually inform our way, maybe how we look at energy consumption in these facilities and help us figure out exactly how we can reduce energy consumption in that context. Now, it's important to also look at several features that are available, not just on the real-time monitoring part, but now on the analytics section, to be able to help us understand exactly how we use our energy and what you can actually put in to be able to help us modify, rather control our energy a little bit better. And I'd like to highlight one specific section. This is the dashboards. I like to look at dashboards as those particular, maybe a tool that provides us with immediate insight, basically a way we can look at specific information without having to actually dig a little bit deeper into the system. And there are several types of dashboards that you can have: the operational dashboard, analytic dashboard, and strategic dashboard. Operational dashboards provide updates in real time. Analytic dashboard to use historical data to actually maybe influence decisions, and strategic dashboard actually track now specific key performance indicators. And let me just take an example of the EGOS, maybe the EGOS program. Our dashboards actually, I think, subscribe to the analytic approach. Where we actually include the ability for the client to actually modify what appears in these specific dashboards to help us to help them maybe be able to get insight, maybe immediate insight, depending on what they want to maybe identify in this particular context. And as you can see, there are two dashboards here. The one is just basically a basic dashboard. This is now preset dashboard that appears to all of our clients, but now the clients have the ability to actually modify the dashboard to come up with specific insights that they would like to see maybe at a glance without having to dig a little bit deeper into the system. Moving forward, what is also available with regards to the analytics section is now unique approaches in visualization. As I've mentioned, there's the heat map that I've indicated that we're able to use in a different context. We're able to help us identify. These heat maps are very, very important to us, and they can help us identify patterns. Basically, they help us identify potential outliers in energy consumption and develop solutions to prevent runaway energy consumption, as I've indicated in the previous, maybe in the previous case study. And it goes a little bit further than that. The heat maps also have added advantages for also directly for energy engineers, maybe in our context. For instance, in sizing solar PV. Now, this is a normal energy consumption trend line. And as you can see, it's very, very difficult to pick out specifically and how pick out how to size for instance, a solar PV system from this particular trend line itself, because sizing it and most sections will provide maybe would raise the issue of potential curtailment, basically scenarios where you are producing more than you actually need. However, drawing from the heat maps themselves, how they segment energy consumption, you can actually come up with a chart like this that looks at average energy consumption across a specific range per hour. It can help us exactly identify exactly what the trend is generally in average of energy consumption over specific hours of the day. And in case where you are looking to set up a grid solar PV system, this particular information from around 8 a.m. to around 5 p.m. would be very, very useful in helping us identify specifically how to size solar PV compared to this particular chart over here, which will give us that particular level of detailed information. So it can help us identify patterns and help us prevent curtailment whenever we size solar PV. Moving on to one of the other sections of real-time energy monitoring that I think most of us have heard about. We've had these buzzwords, predictive analysis, AI, machine learning, and most recently, measurement and verification. Basically, there's a way you can actually use real-time energy monitoring and data analytics to be able to do mathematical modeling to help us identify, to help us do predictive analysis on energy consumption, which will help us identify specific sections that we need to watch out for. And it also helps us in measurement and verification. I'm sure some of us are familiar with the concept of measurement and verification, which is very, very reliant on mathematical modeling. So there are different approaches for mathematical modeling that can be had through real-time energy monitoring. The first one is, of course, is a linear regressive analysis, a scenario where you will have a dependent variable and an independent variable, and maybe develop a correlation between the two, and of course, from the correlation, develop a model that can be used for predictive analysis. Yeah, but this one depends on maybe specifically what you are recording on with regards to energy consumption, and you can actually go a little bit further. Apart from that, maybe the normal regressive models, there's also the possibility of using the autoregressive models. Autoregressive models typically use time series data and maybe pick out patterns in that particular time series data on its own to develop a significant, a very, very complicated model to be able to help you sort of try to figure out exactly how you can predict energy consumption. And one of these that I've had a chance to actually look into is the ARIMA, and basically moving forward is ARIMA. So ARIMA is the autoregressive integrated moving average, and Sarima is a seasonal way of looking at it, basically providing seasonality. So the idea behind all this is using the moving averages to develop a model of energy, maybe of future energy consumption, drawing from data that you use to actually train that particular model. And I'm sure it sounds a bit complicated, but let me try to give you maybe a bit of a look into how it works in practice. In this particular case, there's a section of the system where we're actually trying to perform anomaly analytics by taking in that particular time series data and actually performing an autoregressive analysis on it and be able to generate a model which will predict exactly what energy consumption should have been, and maybe preparing an upper band and a lower band for that energy consumption, or the predicted energy consumption. Now, once you overlay the actual energy consumption on that particular band that you've created using that particular model, you can actually identify specific sections where energy consumption went above or below what would have been expected in that particular context. And as you can see, overlaying this, you can actually be able to do what is called anomaly analytics. Maybe go back to energy consumption, identify specific sections where the energy consumption went significantly higher than it normally is, and be able to see how you can actually figure out specifically what happened during that particular period, be able to help you identify how to mitigate such effects in the future. And the last chart here just shows a sample of regressive analysis directly from the system. This is a scenario where we worked on a data center, rather a small data center, where we're able to log the energy consumption for the AC units and also be able to record the outside temperature and try to see if there's a relationship between the two. And as you can see from the linear model equation over here, this relationship was actually a little bit more viable to be used in mathematical modeling in this case, as you can see with the coefficient of determination around the R square values, drawing at around 0.84, roughly around 84%, showing that there's a significant correlation between outside temperatures and energy consumption for AC units. And I'm going to show you how this particular information here can come in handy in maybe moving forward to a different section called maybe performance analytics in that particular context. So this is the last section that I'm going to maybe define something about mathematical modeling for performance analytics. They're built to actually use the information that we can get from mathematical modeling approaches to be able to do performance analytics, identify exactly how you not just how you're consuming energy, but how well you're consuming energy, basically how well you're performing in regards to energy consumption. And there are two ways that we can actually do this. The first one is KPI analytics, basically the energy intensity analytics, to look at how much energy you're consuming per unit of production, or rather per unit of production. And the regressive modeling, as I've shown you previously, develop a model to actually predict exactly how you should have consumed energy, and overlaying how you actually consume energy to actually identify specifically how you performed within that particular context. And for regressive analysis, there's the actual minus predictive analysis, which I'm going to discuss a bit in a few, and actual minus predictive, the cumulative sum approach analysis, which I'm also going to discuss in a few. And for the KPI analysis, as you can see here, this is now a scenario of the same data center, where now you're dividing the energy consumption, by the temperature, by the outside temperature, trying to see maybe the changes in temperature constitute a significant change in maybe change in performance in that particular context. And as you can see, the fact that these particular values remained almost constant, show that there's a significant relationship between energy consumption and the change in temperature. Basically, a shift in temperature, increase in temperature, increases energy consumption on this particular air conditioning units, and the reverse is true. So that's one way of looking at the KPI, basically the energy intensity for that particular model. And as I've said, you can still use now the regressive analysis. As I mentioned previously, you can actually use the relationship between energy consumption on those particular AC units and outside temperature to develop a model of energy consumption against against temperature, outside temperatures, and actually use that model to actually overlay into what you actually consume, to actually sort of develop a sort of benchmark, maybe a benchmark for yourself to actually figure out exactly how you performed. And one of the ways of doing this, I'm sure some of us were able to, maybe who have gone through training on the energy management systems are familiar with this, maybe subtracting the expected analysis from what the model predicted from the actual consumption, and using that information to actually identify specifically at what point you are significantly above the line or below the line. So basically above the line means that you performed a lot, maybe not good basically. And below the line means that what the model predicted was a lot, maybe was a lot higher than what you actually consumed, which indicating that you performed a lot better. And we can actually go a little bit further on that to look at the cumulative sum analysis in that particular context. Basically, the cumulative sum analysis is the taking of this particular data from the actual minus expected analysis and now editing, maybe editing, apologies, adding the concept of now magnitude to better get an understanding of your results. The point behind this particular chart is to ensure that at the very end, your cumulative sum is appearing below the line to ensure that what the model predicted, you performed a lot better than what the model predicted in that particular context. So that's it with regards to mathematical modeling. However, real-time energy monitoring analytics can help us move a lot further than just energy monitoring on maybe energy management on the side of the client. It can also help us with the audit space. And with the EGOS energy management platform, we are going a little bit further and using real-time energy monitoring analytics to help us with historical analysis for the energy audits that we develop, log data analysis for the energy audits that we develop, and most recently, financial analysis. The idea is that we are able to use some of these tools that we developed to come up with maybe financial analysis information to help us be able to provide significant data, and of course, significant insights for what we're trying to do. And I'm sure a lot of engineers are usually afraid of financial analysis because there's usually a couple of things that engineers don't really understand about the financial analysis and how to calculate some of these metrics, such as the IRR and ROI and NPV, and how they relate with regards to energy consumption. And maybe as you can see, the team at Innovators has been able to take that particular information and maybe maybe digitize it in a way that all you have to do is just put in the information from the project, and the system will automatically generate for us what we need to do. And maybe at this point, I can maybe show you a brief demonstration of the financial engine in practice by showing you one specific particular project can actually do with it. So maybe give me yes. So this is basically the EGOS energy management platform as it is, but I'm going to dive straight into one specific section, which is the financial engine itself over here. I hope you can see my screen. Basically, this is a free part of this particular engine, which I think Ruth will be able to share a link to it for those maybe who would like to maybe give it a go. The idea behind this is that we're able to provide maybe give the engineers a way to actually put in the energy, maybe energy efficiency projects details, and the system is able to cost them and analyze them on the financial approach. So let me just maybe just show you very quickly. For instance, if we were to put in a 200 kilowatt solar PV, kilowatt solar PV system. Of course, the project type is an alternative energy source, so you can indicate that over here. And of course, we're looking in the electrical side, not the thermal side, so you can leave at that point. And the average monthly bill for this particular system, I'm using one of the projects that we've done through this particular system. Average monthly bill in this particular context, for instance, for this particular site was 3,216,332 shillings. And in this case, because we're in Kenya and we can use Kenya shillings details, I can put it that way. Moving forward, I can put in a tariff, basically the cost of energy for this particular site, which is in this case was 16.96. And the inflation in Kenya is usually roughly around 5%, but you can modify that with regards to what maybe your location. The interest rate, this basically the minimum acceptable rate of return can be 8%, 12%, depending on the cost of capital for you. In Kenya, most likely, or rather, most of audits use 13%, which is usually the alternative. Basically, the central bank interest rates, usually somewhere around there. Looking at annual energy saving for this particular project, I put it at as 279,184. This information usually get from PV watts. Basically, you can put in the location data and everything, and the system can be able to show us exactly how much we expect to save. Then the project period for solar PV projects usually size it at around 20 years. We have had discussions around this about maybe the length of project. Most engineers like using maybe the length of the equipment. though some people might look at it differently, but just for this context, I'm going to use the project period basically as the length of the life for the solar PV system. And annual energy consumption for this particular facility was around 2 million, this one, around this particular point here. Yes, this one, around a little over 2 million kilowatt hours on energy consumption. Then, of course, equipment cost usually used at around around roughly 156 shillings per watt for solar PVs. Maybe costing it may be different in different regions, but this is what we've been using so far. In this case, we came to a value of 25,200,000 shillings. Accessories, because on that particular 126 value of 126, we actually maybe lumped in the accessory cost and installation cost and leave this at 0 and 0. And of course, for the maintenance cost, from different analysis and different discussions with different professionals, we usually put it around 2%, basically looking at the cost of potentially cleaning the panels from time to time. Then, of course, the last section, just put in your details, your names, and of course, email address to help the system be able to maybe share some information from this particular project with you. Once you hit finish, the system is able to analyze that project. And first of all, as you can see, first of all, it tells you your project maybe passes the bar with regards to financial analysis. Basically, if the IRR that you were able to generate is actually higher than the cost of capital, which you put in at 35%, gives you the break-even chart, basically your cash flow charts for this particular project. Moves forward to give you, maybe summarize for you the investment analysis, basically a purchase of equipment. And if you had you put in maybe installation and accessories, you put it in there, of course. Then, of course, looks at your saving summary, investment cost, and of course, annual cost of CO2 reduction. In this case, we're still using the Kenyan context, but we're looking to actually widen it to be able to provide a little bit more information with regards to different regions and, of course, their CO2 emission factors, and of course, an annual energy saving, and exactly what that particular annual saving looks at with regards to the cost, and of course, the simple payback. But the meat of the matter here is this particular chart here, which does a full financial analysis. As you can see, the discounting factor we put in as the minimal acceptable rate of return. Maintenance escalation looks at maybe the cost of maintenance or maybe over the period. How much you're going to reduce energy consumption based on what you put in and what solar is going to bring in, around 30% for this particular facility. Your NPV, of course, you know that as long as your NPV is positive at the end of the project, your project is actually viable. And whenever NPV is positive at the end of the project, that will also mean that your IRR is higher than your cost of capital, in this case, which is the discounting factor. So in that case, this particular system develops all that for you, and you're able to actually get that information and potentially just copy it into some of your reports that you are trying to run in this particular context. And then I think at the end, you can leave us a comment, tell us what you think about this particular tool. So that's basically it. That's, maybe in a snapshot, the concept of rather energy consumption. That's the concept of now real-time energy monitoring and analytics with regards to the energy, maybe the energy management field. And then we can go to the final slide right here to just a brief conclusion. Yeah, technology is expanding in the energy, and the energy space really needs to take advantage of this. It's high time we actually take advantage of some of these digital tools and analytic tools and AI, machine learning, put them into some of the projects that we do and some of the things that we do to be able to help us manage energy a little bit better. And a majority of energy management can actually take advantage of some of these tools as I've identified, because you can actually take advantage of it straight from the normal energy management from the client side up down to the energy auditing to be able to provide us with information and better information, more accurate information. And Innovators is playing its part with real-time monitoring, analytics, and automation of some of the audit analytics, which has helped us significantly. As of now, we've actually dropped down the report development timing from around the time that we take to actually develop these reports by around a little bit more than 75% and also increase our accuracy as much as possible. So that's basically it. Thank you for listening, and I think I can return the back to Liz for potential questions. Thank you.
Thank you so much, Martin. I think for that brilliant presentation. I've seen a lot of people asking for this presentation. We do have a WhatsApp broadcast where we share updates on all things on this webinar. I'm sure Ruth will place it on the chat now. And once you're able to join, you'll be able to get all the content that will be in this training/webinar today. And Martin, what a brilliant way to handle the topic on real-time monitoring. You've granted us the benefits, walked us through case studies, and finally do a demo on the available financial tools here and the energy management software that you have demonstrated to us today. It's also the last bit he has shared with us. The financial tool is available online, free for anyone to use, developed by the innovators team. The link is on the chat. And if you want to go even further into energy management and take advantage of real-time monitoring, we do have the Eagles program as well that you can take advantage and jump on today's theme, which is technology updates in energy efficiency. So feel free to ask questions on the chat. We do have a chat master who will note them out. We can also use the raise hand feature as we sort of digest all that he has presented. And for now, I just want to pause a bit and refer to UNREA. In the beginning, I had mentioned that the World Energy Day is in partnership with UNREA, which stands for the Uganda National Renewable Energy and Energy Efficiency Alliance. It's an umbrella organization in Uganda with 5 member associations, and they are here with us today. How excellent would it be to listen to one of them for a brief moment as we gather around your questions on the first presenter. So at this moment, I would like to call on Isaiah, who is a passionate ambassador of clean energy technologies. He is also a project coordinator. He's also a project coordinator last year in UNREA, and we are excited to listen to you. Isaiah, if you can hear me, hello and welcome.
Yeah, thank you, Liz. Yeah, thank you so much, Liz. It's been wonderful listening to you for the last couple of minutes. Yeah, so once again, good morning, ladies and gentlemen. My name is Isaiah Onyu. I offer project support to UNREA. I know Liz has already touched on this, but for the benefit of others who may not know, UNREA is the umbrella body that brings together renewable and energy efficiency actors in Uganda. And since this training and webinar is geared towards energy efficiency, we are very much excited to be part of this team. As we are all aware, one of the targets of the Sustainable Development Goal number 7 is to double the global rate of improvement in energy efficiency. And to do this, the governments all over the world can strengthen mandatory energy efficiency policies, providing targeted fiscal or financial incentives, leveraging market-based mechanisms, and disseminating high-quality information about energy efficiency. The Energy Efficiency Association of Uganda, which falls under the umbrella body UNREA, is doing a tremendous job when it comes to engaging the government on issues related to energy efficiency. Sorry. Of course, as we are aware, industries play a very pivotal role in driving the economy forward. And if their technology and machinery is energy efficient, they use this to increase on their productivity, hence impact positively on the economies. We are confident as UNREA that this 2-day training and webinar will go a long way in helping industry players, especially those in the energy efficiency sector, to get up to speed with regards to technology updates on energy efficiency. And of course, as UNREA, we would like to thank the Institute of Energy Professionals Africa and also the Energy Innovators for partnering with us on this very important event. So we thank all of you for being in attendance. I see the numbers are way high. So please pay rapt attention to these technology updates, and at the end of the day, apply the lessons learned in your various fields. Thank you, Liz.
Absolutely amazing. It's great to hear from the Pearl of Africa. That is Isaiah from UNREA, and he has mentioned such key information that we as the stakeholders, we have a chance in this webinar and training to accelerate efforts to have energy efficiency agenda in more rooms and create more awareness around these technologies in energy efficiency. Thank you so much, Isaiah. He has also mentioned IAPA, who are part of who have partnered with us in this training. And they, as I mentioned earlier, they do offer certification courses, and we do have some training coming up for those who want certified energy manager and certified energy auditor. We will post this information later on the chat. I see the chat is on fire with questions for Martin. And we also do encourage, if you have a question and you want to pose it as well, you can use the raise hand button and you can pose it on video. We do have John Mary, who is asking if you could share the make of the real-time meter or data logger that you use for data capture. Maybe Martin, you can respond on that.
Okay. Hi. Thank you for that question. Yeah, we think we can share that information. I think some of the information is available on the presentation, but I think mostly we mostly use as I've mentioned, the e-gauge, the watt watchers, and some maybe a variety of water meters, which can actually get data into the e-gauge. So, but our main approach is usually using the e-gauge itself. And I think if you visit the e-gauge website, I think some of the information will be available immediately after this particular presentation. Maybe I'll add that information to the presentation. Actually find specifically with this particular meter that we use in this particular context. Thank you. I hope that answers your question.
Excellent, excellent. Thank you, Martin, for that. We do have another question from Mr. Anderson. I don't know if you'd like to pose it. He's asking on how many companies have energy monitoring, and will this be a mandatory in Kenya? This is an interesting question because earlier on we had a poll just to check on where our participants are coming from, the different sectors, and we had about 6% from government. So it's interesting to know that they are in the audience today, and they and even Isaiah mentioned around incentives and policies from the government as stakeholders in pushing the agenda in energy efficiency. So maybe Martin, you can take this up.
Okay, thank you for that, Anderson, for that particular question. As of now, which I think maybe the members of maybe the attendants of this webinar from the government side can attest, it is not exactly mandatory for real-time energy monitoring. However, I think more and more companies are identifying the importance of actually getting this real-time energy, maybe energy monitoring and energy analytics for their businesses. And as at now, just on our platform, we have close to around 100 meters that our system is actually collecting data from, and of course, the other companies that are using maybe different approaches. So it's not exactly mandatory. We're not seeing it become mandatory anytime soon, but I think more and more companies are identifying the importance of this particular approach for energy management and actually taking them up to be able to see how they can take advantage of this particular technology update. Yeah, hope that answers the question.
Thank you, Martin, for that. I think the next two questions are sort of similar, asking on how the Eagles platform that you have demonstrated, how it relates with other technology and monitors, and whether it can collect data from other monitors. There's also Patrick, who is curious on the hardware and units that you had mentioned, whether they are compatible with all energy management softwares. Maybe you can answer both of them at the same time.
Yes, agreed. Thank you for that. In that particular context, you know that yeah, the current Eagles program, it's mostly based on with the meters that I've indicated. However, we've been working on actually now expanding that particular offering to be able to capture a little bit more than just what we are capturing. As I mentioned, there's the COMEX that we're working on. Once we're able to maybe fully integrate it into the system, we can actually have the ability to take data from all Schneider meters and rather that can allow this particular feature. So we are slowly expanding our offering, as I think most companies doing this particular measure actually doing. We're actually expanding our offering, able to capture more meters, and as we expand our offering, we're actually figuring out exactly which specific meters most of the companies use. As of now, we've identified Schneider as one of the main ones, and we're working on it to be able to see if we can now encompass all Schneider meters. Yeah, I hope that answers that question. And on the compatibility of the eGate watches and the other meters that we're using with other management softwares, yes, there's compatibility, but now it depends on the company, because once the company identifies the meter, it has to develop a specific way to actually directly integrate with that particular meter. So which makes this particular process not exactly the fastest, but I think most of the companies that are doing this, inclusive of us, actually on our way to actually expanding our offering, be able to get data from various different meters. So for compatibility, it usually depends on the company and how that particular energy management software is set up. Yeah, but for some of the meters that we're using, they have open APIs. Yeah, for instance, I think eGate has an API, WattWatches has an API, but some other sections, it actually involves a little bit more development of that particular context. But yeah, there is usually compatibility among various different approaches there. I hope that answers that, maybe those questions.
Yes, yes. Thank you, Martin, for answering the questions. We will now have to wrap on this. It's been a brilliant session on real-time monitoring. Thank you so much, Martin. And for the participants that had questions, I see someone joining us from Ghana. Welcome. For the presentations, we do have a WhatsApp broadcast that will be posted on the chat where you can join in and be able to get this information. So now we switch gears to another topic. And our speaker is all the way from Denmark. He is here with us. The topic covers an energy demand that accounts for 50% of the global needs. I'm talking about heat. And the next speaker is going to present to you some special technology on insulation of pipes. Imagine having steam pipes that insulation that does not require maintenance, that lasts for years and years. How interesting would that be? And at this moment, I will now introduce to you Mr. Anderson. He is the owner of EA Energy that is specialized in this pre-insulated piping. And without further ado, I'd like to hand over to you, Mr. Anderson. Hello.
Thank you very much.
Hi, welcome.
Thank you. And it's going to be hard to follow in the first steps of Martin's presentation, but I will do my best.
Absolutely.
Okay. All right, I'll try to share my screen now.
Yes.
That one. Let's see how it works out.
Yes, we can see your screen. Excellent.
All right, first time. Okay. Okay, thank you so much for having me with this very interesting group of participants where we have our chance to explain to you the pros and cons in our approach to the East African market. But can you hear me?
Yes.
Okay, good. So the agenda for today, who am I? The history of how we approached East African community and with our pre-insulated pipe technology. Then we'll talk about the LOGSTOR, the pipes, and the benefits that comes from using pre-insulated pipes. And then we have some time for questions. So I'm E. Andersen. I'm 56 years old. I've been in all my professional life working with energy and energy technology. I live in Aalborg. I have 3 kids and a happy wife, I'm told. I started my own company in 2011, and today I'm sales rep for LOGSTOR in Europe within solar thermal. and industrial applications in EAC. I have a Logstor as product manager and international sales manager. Then I've been where I was working with finding new markets, which I will get back to. So now I've had 10 years with my own energy consultancy company here in Denmark. Well, since I've been familiar with working on finding new markets for Logstor, I looked at some variables when you have to go into a new market, finding a profitable market. We looked at especially Kenya 8 years ago, and there was some indicators that said that we have a kind of blue ocean strategy, meaning that we could see the rising energy demand and the prices going up, and there were not much awareness of pre-insulated pipes. But despite on what you're seeing here, the next pictures, which was, you can say that gave us the idea, gave us the incentive to go and look into the pre-insulated pipes for industrial applications. Pictures you see here are some of the worst pictures I've seen. I must be honest to say that it has not been a focused area in many sub-Saharan countries. So I'll get back to what happens with a pipe when they are left in a condition like this. But you're losing much more energy that we would be able to measure with our normal measuring devices. But again, back to how we looked into this market as a big opportunity is when you have a pipe that is losing more than 47% on the back, on the bottom of the pipe system, then it's almost equals having no insulation. And especially when you look at a pipe system where you have you can see that people been using it as a walkway and now it's open, then you're losing a lot of energy compared to if you're running an air condition and you open the wall or you open the windows. It's almost the same thing that happens. You're throwing up a lot of energy and a lot of money. So again, the conditions of the pipes meant that we thought this could be of great interest for us to enter the market. But as we came in 8 years ago, we came in with new player, new technology. That complicated things because working in most countries, you need to know people. They have to know that your technology. Otherwise, you're already behind in the bus. But we had this kind of not correct approach that we needed to work with the right people and being able to work through organizations and so on. So we had to go back to the drawing board and find out what are we doing wrong. So we found out that there's, I would say, too much focus on the return of investments. Very often we heard people saying, we are not interested if it's not less than 4-5 years, then it's no good to us. And we are very surprised to learn that this was a very short way of looking into making a capital investment. And having said that, we didn't see that the capital investment was prioritized when it came to planning energy transport, and maybe not enough focus on the maintenance costs. But it's difficult both to have a budget with maintenance when we come with a project that takes out something that has to go to the board of management as an capital expenditure. Then we saw another interesting thing, that the CO2 footprint is the interest in bringing it down is rising, especially in the EAC, which is very good since you're using a lot of fossil fuels. And we also believe that there is a need for a rigid system that you install, you forget about it, and it lasts for plus 50 years. But having said all this, we can see that things are moving in the right direction. It's very, very good to hear about that there is a focus on how to collect data, on how to reduce your energy consumption. So it's all going in the right direction. So my previous work at Logstor was to look for new markets with existing products. And we came in North America 15 years ago, and we saw that fossil fuels were taking off around 37% for producing steam alone. And food processing out of 37% equals 57%. So they used a lot of energy. So they started 15 years ago looking at how can we approach on the secondary side. Primary side, you have the burners and you can do the maintenance and so on. But on the secondary side, we knew, or they knew, that the costs for pumping the energy, the steam, hot water applications, cold water, that's very, very expensive. And then the other thing is, if you don't insulate correctly, you will also use a lot of energy on the waste of energy throughout poor insulation. Now, today they have better pipe infrastructure than most of Africa, and you are just getting there with your approach of being interested in how to reduce the costs, which is fantastic. Another thing is, and that's probably not in this group, but standardization and quality installations. The second most interesting thing for us to look at as a supplier is that there is a standard. I'll get briefly back to it later, but also the quality of installation doesn't help much if you have good quality products and they are installed poorly. Then it makes no idea. Okay, presentation of Logstor. Logstor, they are the biggest producer of specialized pre-insulated pipe systems. And it's come to this size because of cost-efficient system that the customer will save on energy consumption. They've been around for more than 50 years. There are 1,400 people working there, and they have around 10 factories in Europe and in China. So it brings them up to a turnover of $360 million US. The pipe system. There are straight pipes. There are curved pipes. That's more for the district heating area. Then they have flexible pipes for small installations, and then twin pipe and double pipe installation where you have supply and return in the same system. The pipe system itself is built of 3 layers. You have the media pipe or the service pipe that can be either steel, copper, PEX, or aluminum. The insulation is the core thing with Logstor. That's where they put in most of their work with optimizing the product. So it's a polyurethane insulation or polyisobate insulation, all depending on the temperature that you're looking at. Then there is a diffusion barrier. I'll get back to that shortly, either of aluminum or a special plastic. And then the outer casing is made of polyethylene high density or steel. Now that diffusion barrier is a technology that Logstor has been working hard, very hard with to find a way to prevent the insulation value to escape out of the plastic jacket. So when you have a normal, that could be traditional insulation or other kind of PE materials that you use as an insulator, then they could be very well insulating to begin with, but over 5 years, it will lose a lot. Up to 60% of the insulation value will disappear throughout the jacket. So, but since Logstor, they have this diffusion barrier of aluminum, for example, you will not see that the energy will disappear. So you will have the same quality throughout the expected lifetime of the pipe system, say 50 years. Another thing that goes into the pipe system or to the Logstor pre-insulated system is that you need tees, and I'm not going to go into details about the European standards with the fittings, but it's just a normal pipe system. You will have straight pipe, you will have tees, you will have bends, and that's necessary when you build up the whole system. Now, another focus technology from Logstor is the joint system. There are straight joints, as you see here, in black and white. Now, why do we have them in white? That's because if you are in a dairy farm, it's important for the authorities that comes to make an inspection on the dairy farm that they will be able to see dirt. And that's why it has to be white. It's a standard, European standard, that if you cannot supply it in white, you're not going into the factory. So that's why we have it in black and white. And of course, we have the straight pipes in black and white as well. Then we have the bending joints and T-joints to fulfill the whole system of joints. How do we install them? Well, we have 2 half shells and we put them around the media pipe, and then we shrink it down either by a shrinkable joint system, or we have the welded system where we weld it with these 2 electrical wires you see here. Then it shrinks down, and then we fill out these holes with polyurethane foam. So I know it's a lot of information about joints, but it's a very important part of our pipe system. And this is basically how it's done. So you have your T, where you branch off to a feeder system with your steam. Then you have the 2 pipes that you weld together. Then you put around half shells, and then the shrinkable joints go down there. Then you have a completely 100% sealed system. No water can go in nor out. And you can have it buried, you can have it above ground. It's good to last for a long time. And then another advantage using the pre-insulated pipe system is that you have the pipe supports outside on the jacket. You put it around the jacket. Well, it means that you don't put a support in touch with the media pipe, because then you have an energy bridge. You have typically a heat bridge that costs a lot of energy, which I will get back to later in a calculation system. This is the one. Logstor, they have this calculation tool online where you could go in and see design tool logstor.com, where you can go and make your own examples on energy loss. But I've put in some data up front where we say we have 100 meters of pipes, humidity 75, ambient temperature 15, wind velocity, very important to put in 5 meters a second. Then you will have 170 degrees Celsius, and you run almost all year. You should have said 8,760. So we have 30 hours for maintenance. No, so that's a full year. You can choose between seamless or welded pipes. Then you take in the dimension of the media pipe. You choose the insulation, how much insulation you want to put on. You choose megawatt hours, and then you get a total energy loss at 100 meters over a year of 44.3 megawatt. Now, here, this is actually a good example on how you put on the supports. You see there, they are tightened to the surface of the roof, and they go all the way around. So you have no energy bridge connecting to the media pipe. Okay. So then we compare it to the existing pipe system, and that is with the normal quality we see in Northern Europe. The lowest factor we can put in is 20 millimeter. You see, the less you put in, the lower we rate the existing insulation. But just all the pictures you saw previously, they are from installations in Kenya and Uganda. And I have several pictures, several business cases where there's probably half of the pipes are not insulated. Condensation pipes, no insulation. So that there's a lot of room for improvement in the pipe systems. But we can only put in as low as 20 millimeters. But at the end of the day, when we put in 20 millimeters and we have outside supports, which we know that you most of the time put directly into the media pipe, then you lose another 25% in energy. And you have one every 3 meters, 3 to 3.5 meters, you have a support. So the total energy loss comes to more than 100 megawatt hour a year. Then we have to put in the energy price. And we did some calculations saying how much is 1 ton of heavy fuel oil, and I estimated to be $600 US. Correct me if I'm wrong, but when we do the calculation and the math, we come into 12 US cents a kilowatt hour. Then we have our serving, per year. This one is actually in euro. It should have said dollars down there. So it's $7,240 a year. Combined to the insulation you use today, that's almost 60% of savings. So there's a lot of, it's a pretty decent return of investment also when you use this calculation sheet. Really, since we have some government people attending this meeting, I have to say something about how important it is to make some standards to protect the end user. We call them ISO 14000 or European norm 253. Never mind all the numbers, but it's so important that you have some quality standards where you say you cannot go into this market without being approved and then use this quality standard. That rules out a lot of bad insulation, a lot of bad installations where you not only lose energy, but within 2, 3, 4 years, you produce a lot of scrap where you have to take out aluminum foiling. Sometimes even the pipes have to be replaced, but the foam, the mineral wool has to be replaced. So you produce a lot of waste. And that's just another benefit with a pipe system that is rigid, that you will avoid this. So basic line, to protect the end user from buying some bad products. That's what the standards are for. So I can strongly recommend that you go by standards, especially to the engineering companies, and say that that is very important. Have your own standards, but have a standard that is benefits the end user. So, as I mentioned, to begin with, the sheer benefits, of course, energy saving, it's money in the bank. You have a CO2 footprint that goes down. It gives the companies a green profile. You have a low or no maintenance, no waste. You can use it as a walkway. You have a long lifetime, at least plus 30 years. Germany, now it says it has to, we have to expect 50 years. It's 100% watertight, ultraviolet resistant, and it's 100% corrosion protected, of course. So, I hope you are still awake, and I hope you have some questions for me.
Thank you so much for that. It's nice to get the perspective from a person from a different region. We seem to be doing quite poorly on our insulation, especially on the industrial side of things. And it's interesting that you have brought forth this technology where we can have pre-insulated piping that lasts over a really long time, great quality, 100% waterproof. And it's interesting how you started your conversation by saying that your entry to the market was met with some kind of cultural behaviors that are in Kenya, or generally with industries where we focus on the finances, quick returns. What would you advise the energy professionals in the audience and the government? What would you advise them to push for this? What would you tell them? In what way should they push for these projects to the decision makers? What tips would you give them in order to push for these projects?
Of course, standards. You need to have some standards. You need to have a green way of looking at what we are doing here. It's a green product, and it has to benefit everyone here. You have to go through the engineering companies have to specify according to, say, Kenya law of energy. We need the companies like Innovators to go out and measure correctly. You've done a great job already. We have some business cases where you're really thoroughly using the tools correctly. But there's so many areas where you can make a mistake. You measure the energy loss from the bottom, where you should always do it on the top and at 3 or 9 o'clock. It makes a huge difference if the temperature is measured to be 29 instead of 44. So that's some of the areas where it's important to find an equal standard how you measure the energy loss. Then I think the KAM need to go out and emphasize members to make a energy audit at least once a year, every second year, to ensure that you're not wasting energy somewhere in the system. We have we have energy monitoring system that we also sell. Last thing, a week ago, we sold an energy monitoring system to Iber Africa, so they can every minute they can see how much if the system is working 100%, and they can get information on their phone saying everything is dry, everything is good. So the monitoring systems are key. They are very important, as well as having and that could be KAM, it could be other groups, where you get a approved installer. As I said also previously, the system is only as good as the installer. So installation, very important, and standards, very important. Then I am sure things will move even faster in Kenya.
Thank you. Thank you so much, Mr. Anderson, for that. To the audience, if you do have questions, please utilize the chat or the raise hand button to ask your question to the speaker. Just about as you do that, I would like to recognize the presence of a very special person with us. She is the CEO of UNREA, Esther Nyanzi. I don't know if you could just give us a quick hello before we resume in the ongoing Q&A. Is she? Okay, okay. I think maybe she will join in later in. But we are really pleased to have the CEO of UNREA join us today. And back to the Q&A that is ongoing. There are a couple of questions on the chat for you, Anderson, and there's one from Patrick Miner. I don't know if you'd like to pose the question, or should I read it out?
Please read it out, then I'll respond. Okay. Then I'll respond on the mic.
Excellent. So his question is that you had done a comparison on the conventional insulated piping against pre-insulated pipes, and the energy savings are visible. He's wondering if you consider doing a retrofit of pre-insulated pipes to replace conventional pipes already installed, considering the capital investment, and how will the ROI look?
All right, that's very good question. We have thought about this. Say we go to a brewery, a very famous brewery in Kenya, and on the cold side they have already installed a pipe, large steel 316 pipe. Insulation is gone within 2 years, and now we come with a pre-insulated pipe where you already have a media pipe. Does that make sense? No, it doesn't. We would never say take your fairly new installation 2 years old and replace it with a pre-insulated pipe of steel 316 with insulation sent all the way from Denmark. So there we would go and say, okay, you need to use polyurethane foam half shells. So we represent a company that can come in and use the existing pipe system, the existing media pipe, and wrap around a polyurethane foam, and then a 100% sealed jacket afterwards. I think that was the question. Is that correct?
Indeed, indeed. I think you've handled it very, very well. We had another one from John Jaggi, and he's asking, please mention something on insulating plastic pipes, conveying cooling water, and can we save energy on that?
Yes, yes. So cooling water, let's see, that would be typically between -6 to 6 degrees. So there you would use, for an example, the PEX pipe from Logstor. I don't think I have a PEX pipe with me, but anyway, you would use a flexible pipe. It comes in coils of up to 500 meters, where you can benefit from having a plastic pipe for tap water, drinking water, tap water. There's a little difference. So you can, yes, you should definitely insulate your pipes. I've seen at a very nice hotel in Mombasa, where they were running plastic pipes, which is fine, uninsulated, and you go into the wall, in through the wall, and up to first level in the hotel, and the condensated water actually destroyed a lot of the installations of the pipes because it was uninsulated. So we always recommend, no matter what temperature you run in the system, unless it's 15 degrees and the outside surroundings are 15 degrees and you have a plastic pipe, then you have to take care of the dew point. You have to take care of the condensation, because you lose so much energy when the pipes they get wet. So yes, Logstar has both PEX pipe and PE pipe and CPVC. So you can choose from all levels on regarding what type of media pipe you would like to have.
Okay. Thank you so much, Mr. Anderson, for answering those questions. For people who have more questions, you can still post on the chat. We are very delighted for that presentation and the product that you have presented to us. Insulation is a place that we may have overlooked, but this training has offered a platform where we have come out knowing better. So thank you so much for that.
I'm coming to Kenya from the 22nd until the 29th. And if people are interested in learning more about the product and get some training about it, I'll gladly give a lecture on this, a product training on this.
Absolutely. That is amazing. Maybe you can just later on share on the chat links to the tool you had shared, and maybe your personal your email that people can reach out to you. But again, we do have the WhatsApp broadcast. We will share details of the speakers that we've had. And that has been our first session. We have had, oh, sorry, I've just seen another question pop in from Joseph Nganga. Maybe I'll just pose it to you. How about insulating plastic pipes, conveying water in the range of 20 to 35 degrees? Is it worth insulating, or is there, as there is little or no condensation, however?
So you have say you have a PEX pipe or PE pipe. They insulate well themselves. And if you have them in a dry environment, I probably wouldn't use insulation. We can find out, but it has to make sense that you have a delta T of a certain size where it makes sense that you prevent the energy loss in the delta T. So running 25 or 35 and the surroundings temperatures, I say 20 degrees, then I would not recommend it. But you can do the calculation, you can do the math with Logstar's heat loss calculation tool, and then you can see how much you're saving. I assume it's above ground when we're talking about this temperature. So, and no, I would not recommend insulating tap water pipes. They have to be above 60 degrees before it makes sense in your area.
Excellent. Thank you so much for answering that so comprehensively. We now want to take a short coffee break, but do not sign out or leave. Just you can just have your video off, and then we meet back at 10:47. But we have an exciting session next. We celebrated yesterday International Women in Engineering Day, and we have a speaker on compressed air. We have a speaker on HVAC systems and water chillers you do not want to miss. So we are going to take a quick coffee break, and then let us meet back here at 10:47. This is East African time. So we're just giving ourselves 5-minute coffee break to stretch a bit, and then grab a cup of coffee. Then we meet here, if that's fine. Excellent. Okay. Hello, everyone. I'm just going to give you a couple of seconds to get back. Luckily, none of you dropped off. You held on, and for a very good cause. The second session has two more speakers and two great topics. And one of them will now take us through compressed air technology. Compressed air is now considered a fourth utility. It is also considered one of the most expensive utilities to run in the industries. And with this, we have the perfect speaker for you. She is Sylvia Chemonges, a project engineer with REN Company, where she helps in designing and installing solutions that help optimize compressed air utilization in industries. So she is the perfect person we want to listen in on the technologies around compressed air. Great. Over to you, Sylvia. Hello.
Hello, good morning. Hi,
Morning. Guys. Hi. Thank you for joining us. Take it away.
Okay, so let me share my screen, share my presentation.
Excellent.
Can you see my screen?
Yes, it's coming up. It's coming up.
Okay.
I can see a shout out on the chat on women in engineering. So more power.
More power to women.
More power. Yes. So
Okay.
yes, it's up. I think now you can go ahead.
Okay, so welcome guys to this presentation on technology updates on compressed air efficiency. I'll tell you a little bit about myself. I'm Sylvia Chemonges. I am a project engineer at REN Company Limited. I have 2.5 years experience in the field, in the engineering field, that is. And before I started working at REN, I was working at a company called Synergetic, where I was working as a process engineer in an oil and gas field. And then from there, that's when I started working at REN. And yeah, I work as a project engineer, as Liz had said. And what I do is design and supervise installation of compressed air systems. So at the end of this presentation, we're going to have a little bit of knowledge about REN, what we do at REN Engineering, some few facts about compressed air systems for those who have not interacted with it. Then we're going to look at what are the challenges that are faced in using compressed air as a utility. And then we also look at what solutions do we use to fix those challenges that we have. And then we're going to have a case study that's going to give us an idea of what we've done at site. And then you can have questions. So as we continue the presentation, if you have any questions, feel free to write them on the chat box. Okay. So REN Company is a company that deals with optimizing compressed air systems. So we do optimization of compressed air systems going in a stepwise process where we look at the solutions as an entire system problem. So we start with a baseline. We come to your company, we look at what you have. We carry out maybe an energy audit or a leak detection audit or a quality audit. And from the data that we collect, we are able to find ways to optimize your compressed air system. So during the optimization is when we figure out which solutions can we provide this client with. And then from there, that's where I come in. We'll design. Some of the solutions require a project, so we'll design and then implement the project itself. And then after that, we make sure that we verify and monitor the installation that we've done for the client to see if it provides savings. Okay. So I'm going to give you some few facts about compressed air systems. So if you've not interacted with it, you may wonder, what is compressed air? So basically, compressed air is atmospheric air that has been taken into the compressor. Its volume is reduced through compression, and as a result of it, it comes out as air with higher pressure. So it's going to be air with higher pressure than atmospheric air. That's why we have compressed air. So from the interaction that's it, you'll be able to see that there are different applications of compressed air. We divide compressed air applications into three major categories. Yeah? We have power applications, process applications, and control applications. So for power applications, is whereby compressed air is used to power tools. For example, you can use compressed air for a jackhammer or a torque wrench. Compressed air is used to power these particular tools. Yeah? Then it helps to provide force or motion within the tool, and therefore you can be able to do the work that you need to do. For example, a jackhammer will be able to drill through concrete as a result of being powered by compressed air. So from there, we go to the next type of compressed air application is in process. So compressed air is used in processes, in the industry processes. We have a lot of manufacturing companies in this country. So compressed air is used, might be incorporated as part of the process, whereby it ends up mixing with the product. So for example, compressed air might be used to carry out drying of the packages before you package the product. So for example, in a food industry, they might want to package, say, milk. So they'll dry the packages before you pour in the milk. So that means that compressed air has touched the package of the surface of the packaging, and it will end up interacting with the product. So compressed air that comes in contact with the product is called process air. And then we go to compressed air that's used for controls, that is to make systems automatic, to control pneumatic valves, control valves, that we call control air. So those are the three major applications of compressed air in an industry. So another fact about compressed air that you might come to realize, it's the total energy, I mean, in terms of electricity that's consumed in the world, compressed air consumes about 4 to 5% of that. So from there, you may wonder, why would you try and focus on compressed air to try and save it? So it's a very important utility in industries after water and electricity. So most companies in the country right now are manufacturing, and they consume compressed air. And compressed air consumes in all those industries. Most people, when you interact with them, you might realize that compressed air consumes about 10 to 30% of their electricity bill at the end of the year. But then, even with this knowledge, compressed air is very misunderstood. Most people think compressed air generation is free. So very little attention is paid to it. So it has a high potential for energy savings. So just to show you how inefficient compressed air generation can be, we take, for example, a 100 kilowatt compressor. So we put in 100 kilowatts of energy. 85% of that energy will be lost as a result of heat and mechanical losses. So only 15% of the 100 kilowatts that you put in is what is going to be used to generate compressed air. But then, because a lot of people don't understand the system, may not actually give it the attention it deserves, 50% of the energy that you put in to generate the compressed air is going to be lost, because the compressed air will be lost as a result of leaks, maybe inappropriate uses where you might meet people cleaning themselves up with compressed air in an industry, or artificial demand whereby pressure tends to increase in the system, but we'll get to it in more detail later. So with that, we realize that compressed air has a high potential for energy savings. So in your lifetime cost of owning the compressor, you realize that 75% of the cost of ownership of that compressor goes to generation of, is lost to electricity costs. So from that, again, you can see how much potential for savings. If we, from this 75%, you can see how much there's a potential for saving if we minimize our consumption. So from that, I'm sure you can already think of some challenges that you might face when you're at site when dealing with compressed air. You may wonder which, you may already think of, let's say, what problems do we have when dealing with compressed air? So we're going to look at the challenges when dealing with compressed air per subsystem. So starting with the supply side, compressed air is divided into 3 sections. There's the supply side, there's the demand side, and the distribution side. So for the supply side, this is whereby equipments are used. These are the equipments that are used to generate compressed air, to treat it, and then store it before it's distributed to the rest of the system and then consumed. So at the supply side, we have compressors, we have filters, we have dryers, and then we have receivers. And on those receivers, we have water drains. The water drains are incorporated in the compressor, the dryer, and the receiver. So to be able to design a good system on the supply side, we need to focus on we need to focus on three things, which is the quality of compressor needs to be supplied to the client, the flow rate at which the compressor needs to be supplied, and then we need to look at the pressure that's required by the machines. So what are some of the challenges that we face on the supply side? So one of the most common challenges that you face, which is a major part in a compressed air system, is leaks. So some sections of the piping have maybe rusted over time. If you've owned a compressed air system for around 5 years, I'm sure there's like around 25% of leaks within the system. So that's a big challenge. Then another thing, the second point, is part load performance. For companies that have varying demand of compressed air, the energy that will be used to supply compressed air, when very little is required, that's when the demand is low, might not be as efficient supplying more compressed air when there's a higher demand of compressed air. So this part load performance is is a big challenge also in terms of the energy that's lost from generation of compressed air. Then the other thing is the third thing is ventilation. So most systems, you might go to most sites, and then you'll see the compressor room is very small and crammed up in a very small space somewhere. The compressor is crammed up in a very small space somewhere. So these compressors do not have adequate flow of air, and then the environment ends up overheating. So the energy, the compressed air generation in such an environment that has high temperature tends to be very inefficient. The compressed air generation in such an environment tends to be very, very inefficient. Okay, so which other challenges do we face on the supply side? Another thing is the equipment selection. Yeah, for example, you work in a food industry as compared to, let's say, a section that requires only controlled air, a company that requires only controlled air. And then the energy that is required to make compressed air very dry so that it can be used in a food manufacturing setting would be higher then that would be used for a control air application. For control air, a refrigerant dryer would work. But so if someone considers taking a desiccant dryer to dry compressed air, there's an extra 15% of energy that you will lose to obtain that very dry air, which is not something that you need to use as control air. So that's another challenge. Equipment selection is usually a big problem. And then we go to drainage of systems. So most of the time you'll meet people there, you'll meet most sections that have manual drains. They rely on people to go and drain the condensate within their compressed air systems. So such systems are very unreliable because, I mean, we are human, you tend to forget to drain the receiver. So as a result of that, condensate ends up going back to the system. Or in the process of draining compressed air, in the process of draining the condensate, you also lose compressed air. So yeah, those are some of the challenges. Then from there, we look at the distribution side. So from the supply side, we go through to the distribution side. So the distribution side is where we transport compressed air from the supply side to where it's needed. So the distribution side encompasses the piping system that you use. A very key component in selecting the correct, designing a good distribution system is the quality of compressed air. You need to look at the quality of compressed air supply, the pressure, and the quantity, and the flow rate. Yeah. So those three components will be able to help you select a good distribution system. So what are some of the challenges that we face on the distribution system? So again, very, very important problem that goes around within most industries is leaks. Leaks is a very major part of compressed air systems. So what happens if a company has leaks? Most of the time, you'll meet people. Most people will tend to crank up the pressure in their compressed air system so that they can be able to generate adequate generate enough pressure to supply the machines. So the issue with that is that the amount of compressed air that's going to be lost as a result of cranking up the pressure, because the flow rate of compressed air is going to increase automatically the moment you increase the pressure. So you're also increasing the pressure at the leak point. So at 5.5 bar, for example, we have here, let's say you have a 1.6 millimeter leak and your pressure was 5.5 bar. The moment initially at 5.5 bar, it has 2.5 liters per second of, sorry about that. Oh, sorry. Just a second. Okay, so the pressure, sorry about that. So the pressure at 5.5 bar, the leak at the flow rate of the leak at 5.5 bar is lower than would be at 8.3 bar. So instead of cranking up the pressure, it would be ideal to actually just fix the leak. You will have you'll lose 40% more by increasing the pressure. Then another challenge that we have on the distribution side is usually in terms of the design. So you go to site and you see a piping system that has bends everywhere. There's an elbow here, elbow there, teeth joint here, smaller pipes there. The piping design is usually a big problem. So as a result of constricting the flow of compressed air, you end up having high losses, pressure loss within your system. Then as a result of that, again, we meet people trying to compensate that by increasing the pressure within the system, of which you would just fix it by using the proper design, using the proper pipe size as required. So anyway, we'll get into the solution side. Another thing that we see at site on the distribution side is usually the type of pipe. So you might go to a food industry, and obviously for a food industry, for a compressed air that end up interacting with products that you're going to consume, the compressed air has to be of very high quality. So you'll end up meeting sections, companies they're using GI. So GI or black pipes are very prone to rust. And then imagine that you carry that rust and the condensate within the system into your products, and you'll end up having a lot of issues in terms of meeting the standards that are required. You might be told, no, we need you to go back and fix products again. So you'll end up losing more by using by using the wrong pipe material than selecting the correct type for your application. So after the demand side, we can look after the distribution side. So we can look at the section where compressed air is being taken to, where it's being used now. That's the demand side. So from the demand side is where we've talked about the different types of compressed air, where it's used. So at the demand side, you can be supplying compressed air for either of the three requirements. It can be for power application, whereby the quality of compressed air obviously won't be as high as that which is required to supply for process application. Also from there, you have compressed air supplied for instruments, won't definitely be as high as for food manufacturing. So that's the demand side. From there, you can wonder, what are the challenges that we face when supplying compressed air to the sections that require compressed air itself? So another thing that we face, big challenge on the demand side, again, leaks are everywhere. I won't delve into that so much. We've already talked about it a lot. The next thing would be artificial demand, of which I touched on when we were starting. What happens when you supply compressed air at a higher pressure than what the machine needs? Let's say your machines need 6 bar. You supply compressed air at 7 bar because you have leaks and they need to compensate for that. Your machine will consume, yes, that 7 bar, but it does not need the 7 bar. That extra 1%, that extra 1 bar results in 7% loss in energy within your company. So that's another challenge. And then high pressure drop. High pressure drop occurs when you use equipment, let's say filter regulator that causes a lot of pressure drop just before the machines. And then another thing would be maybe using very long constricted pipes. You'll meet people supplying compressed air from the drop point, maybe 1 meters away to the equipment, using polyurethane pipe. So that pipe is really small. Let's say it's 8 mm, and you're supposed to supply compressed air to the machine. The constriction results in a lot of pressure loss within the system. And then another thing on the demand point we mentioned earlier was inappropriate use of compressed air. You meet people using compressed air to clean themselves up, yet you can go and use water to clean yourself up or just wipe yourself off. Yeah, so that's a big challenge in industries. So from all these problems, how can we solve this to minimize our energy consumption? So we look at some of the solutions in our compressed air industry that we can use to solve these problems. So we've mentioned, as we mentioned on the supply side, we have a lot of challenges in terms of leak, part load performance of the compressors, then poor ventilation, poor equipment selection, and maybe lack of water drains. So what are some of the solutions that we can use to solve these problems? So the first thing would be to monitor the system. carry out monitoring of your compressed air systems. From the monitoring, we can be able to look at how much energy you're consuming to supply compressed air to your machines. In case of any spikes or changes in requirement, the demand in your system, then you can be able to figure out how are we going to fix this to reduce the energy consumption. Maybe we need to change the machine, maybe we need to improve on the piping, maybe we need to fix leaks. Yes, so monitoring is a very important part of minimizing losses within your compressed air system. Another thing that you can use to solve the issue of part load performance of compressors is using varying speed drive compressors. So a variable speed drive compressor is one that varies the output of the compressor to match the demand from the plant. So if the compressor is supposed to supply 100 liters, but at noon they require 20 liters per second, then the compressor will reduce its output to match that 20 liters per second. If the demand increases, then the compressor increases generation of compressed air to match the demand. So variable speed drives tend to save your system around 35% more by using this as compared to a fixed speed compressor. Because of the fluctuation in demand, it's going to save you a lot of energy to match the demand that's required. So for systems that have more than one compressor, maybe let's say 2, 3, 4, 5 compressors, you need to have a master controller. So this is a device that helps prioritize which compressors can run depending on the performance that's required at the plant. So if you have 3 compressors and your load increases, let's say from 30 to 40, this master controller will figure out which compressor do I need to run to be able to generate this much compressed air within the system. So having a master controller helps a lot for most companies that have around 3 compressors or more. From there, another thing that can help us is to incorporate water drains. We had mentioned the issue of manual draining. So you'll go to most industries and meet people draining condensate from their receivers manually. So the issue with that is as you drain, you lose compressed air. Also, the number of times you drain sometimes depends, because the amount of condensate in the air varies with the humidity and it varies from month to month. So you can say, let me go and drain compressed air every 5 minutes or every 1 hour. But then the amount of condensate that has collected, let's say in June as compared to July, won't be the same. So incorporating an electronic water drain helps in the sense that it senses the amount of condensate within your system and drains only the condensate. It does not drain any compressed air. So that's why we have a zero loss electronic water drain. You will not have any losses in compressed air within your system, and it only releases condensate after it has reached a certain level. So it's very efficient. And then the other thing would be to have adequate ventilation. Maybe incorporate ducts for those areas where ventilation is not enough, it's not well ventilated. Some people might even think of recovering the heat that is being generated. We mentioned 85% of energy from a compressed air system might be lost to heat and mechanical losses. So some companies may consider recovering heat, say for heating, for those countries where it can get very cold. You can use the heat generated from the compressor to heat up the environment. And then the other thing would be for companies that use water-cooled compressors, they can use the water generated to preheat products. Say, for example, a milk processing company can use the hot water to preheat the milk for sterilization, for example. So the distribution side, we saw that the major problem on the distribution side is leaks. Leaks and poor design is usually a major problem. So how exactly can we solve this problem on the distribution side and the demand side? So a major part that we consider is to fix the leaks. So before fixing the leaks, what do? You have to identify where the leaks are, quantify how much you're going to save from these leaks, and then figure out how to fix them. So what we do is we use an ultrasonic leak detector, because from the release of leaks, that turbulent flow from that particular leak releases some ultrasonic sound that can be detected by the device. You cannot hear it, but it can be detected by the device. So what after that, it quantifies, converts that sound to flow rate. And from that flow rate, we can be able to see how much in terms of money you're losing to leaks within your system. So leak detection. The other thing would be to incorporate using leak-free pipes. So we've said GI pipes, black pipes, they're very prone to rusting. And those threaded connections end up weakening over time as a result of rust over time. So it would be interesting to consider using aluminum. It's relatively more expensive, but in the long run, it's going to save you, because the connections of Airnet aluminum pipes are push fit. You just put the pipe into the fitting, then lock it. So it's a little bit more like what Anderson do with their insulation piping. You just put the fittings together, connect them, then lock them. And then these pipes are leak-free. You won't have any leaks. The pipes' internal space are very smooth, so pressure losses within these pipes are also very small. Then what should be the next thing to consider is measuring flow rates to individual machines. Then from there, you can determine if there is any losses to these particular machines. Okay. From there, we go to the demand side. On the demand side, we noticed that we had challenges in terms of inappropriate use, artificial demand. And so how exactly do we fix these problems? So for inappropriate use, maybe it would be best to try and, first of all, educate people who work within your company. And from there, figure out ways in which you can minimize your compressed air use. Next would be, for applications that you need to carry out cleaning, consider using a blower instead of compressed air. Because compressed air, the amount of air needed and power needed from a blower would be less as compared to using compressed air. So if you must use compressed air, then consider using nozzles instead of open blowing pipes, because a lot of times we go to site, we meet people with open hoses blowing sections. The amount of compressed air released from those open hoses as compared to using a nozzle would be very, very small. So what happens with this nozzle is they entrain air from the atmosphere and also use compressor. So the amount of compressor that's going to be used will be less as compared to using an open blowing hose. Another thing is for companies that carry out constant, carry out a production constantly, production is continuous, it would be best to consider ways in which you can minimize your compressed air use. So for example, there is a valve called KTW valve that generates compressed air in pulses. So what it does, it opens, closes, opens and closes. So generating compressed air in pulses helps minimize the amount of compressed air that's being consumed. Another thing would be for sections, manufacturing sections that do not need compressed air at a particular time, the valves can open and close. There's valves that can open and close when compressed air is required at the use point. So incorporating any of these two valves, will be able to save almost 50% of the total compressed air that you require within that section. So to minimize, the next section would be to minimize the pressure drop within your system. So how can you do this? You should consider using equipment that have very low pressure drop across them. So for example, you use a filter regulator that has very low pressure drop across it, or consider using hoses for sections to supply the machine for shorter distances, or in a bigger size depending on the flow rate required by the machine. Okay. So in summary, we can say one of the major, most important things to consider in improving your compressed air system would be to reduce the amount of leaks that are present within the system. Leaks are a very quick win for you if you choose to fix the leaks within your system. And they are the section that consume the most compressed air for those people who maybe run for around 5 years and maybe don't carry out constant maintenance within our country, that is. Another thing, in summary, would be to consider using a good overall design of your system. So looking at the supply side, you look at which compressor do I need? Is my demand varying or is it fixed? If my demand is varying, consider using a VSD. If my demand is fixed, then consider using a fixed speed compressor. The size of piping, we look at the size of piping. How much flow rate am I supplying from the compressor? What pipe size is required for this particular flow rate to minimize losses, and which will have minimal loss. The filters and the dryers that we select, am I able to have minimum pressure drop across these equipment? So it's very important to consider the overall design of your system when trying to improve your system. Then for companies that may need to reuse the heat that's being generated, we said we lose a lot of heat of energy in terms of heat from compressed air systems. You can consider recovery. So that would be through, as I said, using the energy from the hot air to heat up spaces, or using the hot water to heat up other products, minimize your energy consumption. Yeah, so variable speed drives are very energy efficient compressors. The 90% of our companies that carry out manufacturing have a possibility of using a variable speed drive. So there's a big section of this that needs to be considered over time. Most people still haven't gotten to that point yet, but it's getting there with time. So, and then another thing would be to reduce the overall system pressure. Reducing your overall system pressure reduces the artificial demand. If your compressor requires 6 bar, supply 6 bar. Do not supply 7 bar. That extra 1 bar is going to cost you a lot in the long run. And then for your supply side, also optimizing your storage would be very important. Optimizing your storage helps you minimize the number of times the compressor is going to run to meet the demand. So what the receiver does, it buffers supply from the compressor. So compressor runs, supplies enough compressed air from the receiver, then it stops running. So air is going to be consumed from the receiver. So energy consumption from the compressor is going to be low. And then basically just eliminate any pressure losses that you have within your system. That would be through minimizing the leaks. That would be through using proper pipe sizes, proper material. Yes, consider all those things, and overall you can have a better and more efficient compressed air system. Okay, so to show you an example of a company that we've done this is we had a client in 2018. So this is a independent power generation company. So what they had two fixed speed compressors. The energy they were consuming to supply compressor, because they needed compressor for control air, that is for their instruments. But the energy they were consuming was twice what would be required to generate compressed air, the amount of compressor they needed. So what we did is you carried out an energy audit. Then from there, you could look at we saw the energy consumption, figured out ways in which we can minimize this consumption. So after carrying out the energy audit, we recommended that the client fix their leaks, incorporate a VSD compressor because they were using fixed speed compressors, and carry out continuous monitoring of their system. So from that, we were able to recommend them a 15 kilowatt VSD compressor, which was installed in 2019. And then we installed a power meter, an inline flow meter, and a monitoring system from CAMS. So from that, you can be able, from the monitoring system, we can be able to look at the key parameters, that is the pressure, the flow rate within the system. And then from there, how much power are they consuming and are they operating efficiently? And they were able to save around 800,000 shillings within a year of operation within the changes that we incorporated. So with that, I'd say thank you for listening to my presentation.
Thank you so much, Sylvia. That was absolutely brilliant. I was literally taking notes the whole time. I love how well you have taken us through, even for people who aren't very conversant with compressed air. You've really taken us through right from what is compressed air, the facts around it, what are the challenges on the ground, what are the solutions. I love how your presentation has also sort of mirrored some of the information that we've been getting during this session from the rest of the speakers. You've talked about real-time monitoring of compressed air. We had our first speaker talk about real-time monitoring of energy. You've talked about pipe designs. Anderson also had a lot to talk about the current situation of pipe designs and our insulation here in East Africa. It's absolutely lovely to see all that. So now it's a question and answer. So I would allow us to just digest that information. If you have questions, use the chat, use the raise hand button. But as you do that, I would like us to do a short exercise. Maybe we can have, maybe Sylvia, you can stop share. Excellent, excellent. So maybe let us have a short, quick activity, and I'll request Emily to go ahead and share the activity. I want you to look at what is on the screen. I don't know if it's clear enough. Oh, is it clear to everyone? Okay. Okay, I just want us to try and count the number of squares that we are seeing on the screen and post on the chat what your answer is. Just take a few minutes to, excellent, yeah. Just take a few minutes to count the squares on that you're able to count. So about 10 seconds, 10 seconds, 8, 7, 6, 5, 4, 3, 2, I'm getting 34, 26, 44, and that's it. It's done. We are ranging between 24, 25, and the highest was 44. Emily, if you could show us
how many squares do you see? It can get a little confusing to keep track when you start the counting, but we can keep track visually using Doceri. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, and the last square is 40. We've used Doceri software on the iPad to visually keep track of the squares that we've counted to solve this puzzle.
Thank you so much, Emily, for that. I'm seeing people with 44. Guys are multiplying squares. I saw 16. Oh my goodness, 24, 25, 20. The guys of 44 will really have to tell us how they got to 44. Very, very interesting there. That was just a quick exercise to, let me see who got, I don't know. Let me see, was there anyone with a 40? I saw a couple of 40s, Joseph Nganga, and is it just Joseph Nganga? Maybe you can just help me look through, but I have noticed Joseph Nganga, shout out to you. Excellent for winning that activity. The last time we had an activity, the person won a branded prize from us. So congratulations, Joseph Nganga. We now go back to where we were on compressed air. There were a couple of questions for you, Sylvia. And there was one from Mubarak who was asking, just a moment. Yes, on the specific instrument that you are using to log the compressed air system to capture parameters on power, energy, flow rate, and the pressure of the parameters you had mentioned. Maybe you can take that up.
Okay, so when it comes to trying to monitor the amount of flow rate, pressure, or volume, and power, we use for pressure, flow rate, and volume, we use the flow meters. There is a flow meter that can be inserted. It's called an probe flow meter, goes into your compressed air piping and then measures the flow rate. Or we can use a flow meter that is inline. You use it along your piping to collect the data on the pressure and the flow rate that is being consumed. And then on the power side, we use a power logger. So you just take the data of the power that matches the flow rate. And then from these, you can collect all the data and match your system, know how much you're consuming in terms of power and energy and flow rate at a go. Or that is for people when you want to carry out monitoring. And for those people who need monitoring, we use a CAMS monitoring system. So from that, you can get real-time data on how much you consume in terms of flow rate, volume, and power also.
Thank you so much. We had promised you a webinar on technology updates on energy efficiency, and that is what we are providing. All through, we have been getting exposed to more and more technology. We are currently on compressed air. We had another question from Gloria, and shout out to Gloria, who is part of our YEEP program, Youth in Energy Empowerment program that is currently running in Kenya. She's part of the first cohort of 10. Her question is on the ultrasonic leak detector. She's curious on how to use it, the expertise, and how simple it is to use it. And then maybe I can just sample this with another question on how efficient can compressed air be if you're doing it well? What are the ranges of efficiency that we should expect from an excellent system?
Okay, so to answer the first question, where was it? About
yes,
ultrasonic leak detection?
Yes.
Maybe you can give me her data, can give her more information on how much it would cost to get the ultrasonic leak detector. And no, it doesn't need a very superior expertise to deal with it. It's a device, you can figure out how to use it. Yeah, anyone can figure out how to use the ultrasonic leak detector. Yeah.
And then on the second question on what should we expect the efficiency of an excellent compressed air system to be?
I can't give you the exact number, but I can tell you, you can save up to 30% of the energy that you're consuming if you fix leaks. First of all, let's just start with leaks. If you fix leaks, you already save yourself 30% of the energy that you consume. Yeah. And if you consider shifting from, it will depend on what you're using. If you consider shifting from a fixed speed to a variable speed drive, you will save yourself around 50% of the energy that you consume.
Absolutely amazing. Thank you. Thank you
Yeah.
so much for that. Sylvia is still reachable. A lot of positive comments on the chat. We will on the WhatsApp broadcast that we had posted earlier. I think maybe we can do it again on the chat. You will be able to get more information on the speakers, get connect with them. We also have the World Energy Day website where we do upload previous reports. This is sort of the fourth roundtable that we are having. We've had 3 so far. This has been a hybrid, however, since it's a training session, it's focused on capacity building, and we are so glad for everyone joining. It will be a 2-day session. We have another session tomorrow. For today, we have one more speaker remaining, and it's been an absolute pleasure to have you, Sylvia. Thank you for your presentation and your comments.
Thank you for having me.
It's been such a pleasure. So on to our last speaker. He is a trained consultant and a trainer in energy efficiency and conservancy. He's also a trainer with, he is a certified energy manager and a certified measurement and verification professional. And I'm trying to read them out because there are so many. Once attached. Our partners, IEPA Institute of Energy Professionals in Africa, is the representative of the International Certification Body Association of Energy Engineers in Sub-Saharan Africa. They do offer this certification courses, and as innovators as well, we are having trainings coming up, and I will post details on the chat as we continue on the upcoming trainings that we have. So one is an online one, a certified renewable energy professional, that will be happening in July. I think as I speak, we'll probably just post more information on that. And we also have another one that will be physical. Apologies. Yes, the other one will be the CEM course. That will be an in-person training towards the end of July, 26th to 31st. We are going to post in the chat. You can also reach out to Karen if you are interested in these courses. And as I was saying, I was speaking about the next speaker, and he has a wealth of experience. Africa in 2016. He is going to take us through an interesting part of industries, and that is the HVAC system, with a special interest in chillers. His name is Eustace Moreithi. Eustace, if you're there, hello, welcome. We are more than excited to listen to you. Hi.
How are you?
I'm good, I'm good. Yes, I can. It's such an honor to have you join us today.
Okay, can you hear me now?
Yes, I can. I can clearly. You may now take it away. Okay.
Let me share the screen. I think this is the right screen. Check.
Yes, we can see your screen.
Okay, I won't repeat my name, but I'm going to deal with how to improve energy efficiency in air conditioning systems, especially chillers, mainly in chiller systems. So, as you are aware that the chiller systems are used to cool water, and that water is used for either space cooling or product cooling in manufacturing systems. And the chillers are one of the most energy consuming equipments in any facility, especially in factories and in building services. You can use chillers to cool water for even conference halls and so on. And one of the major thing is there are very many energy savings opportunities in chiller systems, because unless handled very well, they produce very, very good areas of energy wastage. And without wasting time, that's how a chiller looks like without being connected to any other system. And this one is our water-cooled chiller. And so as we have seen, the chillers are used in cooling water, and that water is cooled for product cooling, either in manufacturing or in space cooling. You find them in oil refineries, you find them so much in milk factories and data processing centers. And especially in Kenya now that we are embracing a lot of IT, many people are going to be setting data processing centers and servers which were required to maintain a certain amount of temperature. And the chillers come in handy in that. So mainly in a chiller system, we have the chiller itself, we have the space being cooled, we have pumps, we have pipes, we have in some cases, if it's water cooled, we have a cooling tower. And for the other chillers which are air cooled, they're installed with air cooling systems. We have pumps in the chiller side, we have pumps in the cooling side. And for you to understand is the chiller, to understand a chiller, you need to understand what we call the refrigeration cycle, which occurs within the chiller itself. So you can see there is a chiller with other auxiliary units, the cooling tower, we have the space being cooled, we have ducting systems, we have piping systems, we have pumps, and so on. So in any of these equipments, there are so many areas of energy saving energy opportunities. And even the chiller system, you can see I have introduced some fountains in the corners. We are going to talk about them later because they also form some of the areas where you can use to save energy in chillers. Also, we have things like air handling units. They are used in conjunction with the chiller, where the cooled water passes through an heat exchanger and you cool air. So in a nutshell, that's the way a chiller HVAC systems look, water chiller systems look like. So types of chillers, as you have seen, we have air cooled and we have water cooled chillers. Mainly the water cooled chillers are used for heavy duty where you have a lot of load, and the air cooled chillers relatively small loads. So in any situation, before you decide on the kind of chiller system you're going to use, you should know the amount of load you are using. Because if it's a very big load, you need to employ a water cooled chillers. But for relatively small loads, it will be inefficient to use the water cooled chillers. So you have to check, and we are going to show the ranges of loads, cooling loads, so that you can understand the situation. You have to use the air cooled chillers. In air cooled chillers, you can see there are fans. These fans are the ones which are used, like instead of using a cooling tower, which is in a water cooled chiller, that's what you have in the air cooled chillers. So improving chiller efficiency. One of the areas you have to check on when you want to improve the efficiency of water chillers, you have to check on the technology. And that's one of the biggest reasons we have this webinar, so that you can see the various technologies, upcoming technologies, because as technology improves, you also need to improve. So you have to always check on the newest technology, the most efficient technology. The other one is the operation through the process. In a chiller systems, you don't concentrate on the chiller part itself. You have to check on the chiller, the operations, the areas which are being cooled by the water, the chilled water. You need to understand the dynamics of the operations in those areas. And the other most important thing is to check the controls. Controls in energy efficiency systems, controls are very important because after understanding the operations, you need to see on how you can control how the chiller comes in, on, off, and on, so that you can know at what point to switch off and what point to switch on, so that you can save energy. So before we concentrate on, go on the chiller systems, you need to understand the refrigeration cycle, because that forms one of the most important parts for the chiller efficiency. The refrigeration cycle looks like that, but this where you consider what you call TS diagram, that's temperature entropy diagram, or you can have your refrigeration cycle represented in a pressure enthalpy diagram, which are, for me, I like mostly using the TS diagram, the temperature entropy, but all of them are the same. You see in the refrigeration cycle, this is a TS diagram, this is the schematic figure. So on the evaporator side, where you do the cooling or you do the chilling of water, it's represented by this bottom line 4.1 in both the pH and the TS diagram. The compressor area is represented by the 1, 2, and this is the condenser area where you throw away heat which you have absorbed. And this the throttling valve or the expansion valve, which is used to change. You see, once you cool the refrigerant, in the cycle, the refrigerant moves within the refrigeration cycle, in a closed cycle. So once you cool within this range, and this red line is what we call saturation line. On this side, it is vapor saturation line, and on this side, it's the liquid line. At this point is the liquid line. So the expansion valve changes the pressure of the liquids from very high pressure, let's see, from very high pressure to low pressure, so that it can cool and be used now at low pressure. It can now be used to absorb the heat from the cooling space. So on that case, you need to, the chillers have got one area in the refrigeration cycle. At the compressor is where you have most of the energy being consumed. You need air, you need electricity to run the compressor. And that's one of the areas where you can improve, or you can change, you can improve on energy efficiency of the chiller, because it is the compressor which directly consumes the energy. In most cases, at the evaporator and the condenser, here we have heat exchangers. So in the refrigeration cycle, you don't have any energy consumption here. What you have is the heat exchange between the media being cooled and the refrigerant, and the cooling media. In this case, if it's water, in water cooled chiller, you have water. If it's air cooled chiller, you have air. So one of the areas you have to concentrate on mainly, and the reason why you have to understand the refrigeration cycle, is to know the power. The length of this line represents the power, the input power to the chiller. So if you can be able to reduce the length of this line by offsetting probably the temperature here, or improving the rate of heat exchange between the fluid being cooled and the refrigerant here, you can be able to either go at a higher temperature, you operate at a slightly higher temperature, and that one will reduce the power input to the compressor, by the compressor. At the same time, if you monitor the conditions at the condenser, where you are using it to the cooling media, you can be able to monitor the temperatures. Probably if it's air and it's on a cool day and a cold environment, the air is cool, you can be able now to monitor that air and reduce the amount of work being done by the compressor, because you can operate at a slightly lower temperature by doing what we call condenser reset, condenser temperature reset. Here you can do what we call temperature reset. At the same time as the compressor, you can be able to get the most efficient compressor, which has most a good efficient motor and the compressor itself. From there, you can be able to minimize the amount of energy you are drawing from the electricity mains line. So that's the diagram. That is the schematic diagram of refrigeration cycle, where you have the evaporator, the compressor, and so on. That's what you have been explaining in the previous. So potential areas of improving energy efficiency in a compressor, in a water chiller. One of them is to do the compressor retrofit. You have to check your water chilling system and the cooling system, and check the amount of load. If the amount of load is not very high, use a small chiller. But if it's very high, you need to use a different type of compressor, probably the centrifugal compressor or the screw compressor. Reciprocating compressors for small chillers are more convenient than the, say, for example, centrifugal compressor. So when doing your energy audit, after discovering that the amount of cooling load which is required in that system, or during the design of a compressor of a water chilling system, if you discover that you don't have very high runs, you need to check it, because the efficiency is not just energy efficiency, it is also about the amount of money you spend in running the system. So the other thing is to get the most efficient compressor for that system in the market. The other one is the other area of energy efficiency. You can use VSD, depending on how the load, your cooling load is varying. In most cases, you find that the temperatures like in tropics vary from morning to evening and at night. So you need to know when you are operating your system and see the varying load and be able to use your controls in conjunction with a VFD, the compressor, so that when the load is not very high, either you can run at lower speeds or you can run at a smaller compressor, or you can run one compressor if the water chiller has multiple compressors. So a VSD will be able to reduce the speed. And in most cases, you must be very careful when using a VFD, because it is almost inefficient if you are reducing the speed of a motor less than 20% of the original speed. So you need to operate within the 20%, or else from there you get a relatively small motor. You can do what we call chilled water reset in the evaporator side, where probably in your demand for the cooling load, you don't require water at very low temperatures. Probably instead of chilling water up to 6 degrees, you can use water up to 8 or 10 degrees. And that one will reduce, as we say in the size of this line, reduce this line, which is proportional to the amount of work you are doing, the amount of work being done by the compressor, or the energy being consumed by the compressor. The other one, you can do the condenser reset. At the same time, as we said, you need to understand this diagram. At this condenser reset, probably you don't have to release, you have to check the temperature of the refrigerant and the temperature of the environment, so that probably you don't have to have water being cooled, the cooling water, especially for the water cooled chillers. You don't require very low temperatures. You can be, for example, instead of releasing heat at say 23 degrees, you can design to heat at 25 or 30 degrees, and that one can save a lot of energy. And the other part is your scope of condenser reset. The other one is condenser evaporator cleaning. So the efficiency of the refrigeration cycle of the chiller will depend on the efficiency of heat transfer between the evaporators or the condensers. You see here you are cooling water using a refrigerant. So the efficiency of the heat transfer between either of the two will determine the efficiency of the compressor. That will reduce the number of times the compressor is running. So you need very clean. So you need to be monitoring the cleanliness of the evaporators and the condensers so that you can know at what time to stop your water chiller and do the maintenance and cleaning. The other one is expansion valves. Mainly we have what we call thermal expansion valve and electronic expansion valve. Currently, the thermal expansion valve are the old ones, and you find that they use a fluid to detect the changes in temperature of the refrigerant, so that they can be able to control the amount of refrigerant which is flowing in the cycle, the refrigeration cycle. You find in this refrigeration cycle, immediately after the condenser, the refrigerant becomes a liquid. Immediately after 4, we have like a reservoir to hold some of the refrigerant. And that refrigerant is released to the evaporator depending on the cooling load which is in the evaporator. And that one is checked by checking what we call the superheat. The superheat. If you look at this point after you have cooled your water, the refrigerant gains some heat, and before you compress it, you need to make sure that it's in vapor form to avoid destroying the compressor, because the compressor will get destroyed if you compress it in liquid form. So you need to superheat it a bit. So the work of the expansion valve as a system is a detector. So you need to get to use a modern expansion valve. Instead of using a thermostatic valve, we use what we call an electronic expansion valve, which is being controlled by like a servo motor. The other one is air-cooled chillers. You need to check the fans. You can see these chillers, the air-cooled chillers. Here you have fans, and in most cases you find that in most chillers these fans are running throughout. So you need to get fans which you can reduce the spins, or you can be able to run some fans you can be able to switch off some fans depending on the cooling load. You see, in your refrigeration cycle, in your system, if the load in the air handling units is not much, you need to be able to switch off some fans to avoid overcooling the refrigerant for no use. That is in that system. In such system, you need to In such systems, for the air-cooled chillers, you need to accompany it. You have a system which is incorporated to control the fans, and then based on the chilled water, the temperature of the chilled water. If you don't require a lot of chilled water, also at the same time, you need to accompany it with chilled water. So when you do the chilled water reset and you find that you don't require water at very, very low temperatures, you also need to reduce the number of fans which are running or the speeds of the fan. And there you can be able to save some energy. The other one is you need to employ free cooling. In cases the environmental conditions, the surrounding conditions are not very hot, that one can, instead of continuing running, especially for water-cooled water chillers, like this one, like this are water-cooled, you find if the outdoor air temperatures are very low, you can be able to cool the space, for example, using the air. And in such a system, you don't require very low temperatures here. And then sometimes you can even bypass the cooling, the chiller, the compressor of the chiller, and they use the water cooled in the cooling tower directly. I'm going to show you the next diagram later. So that's where you employ the free cooling. So you have seen free cooling is where you can even switch off the compressor and the old chiller and use either the cooling tower or the external conditions, air with the external conditions. Then the controllers and the fittings. Whenever you do your energy audit and find you're using like old fittings, you can employ new fittings, especially the expansion valves, which are more efficient. And you need to have automatic controllers, which can be able to control the chilled water, get information of the temperature of the chilled water, and either switch off the compressor, switch off the fans, and in such a system, you are going to save energy. The other one is the cooling tower, pumps, and HU. These are auxiliaries which are used with the water chillers. As we have seen, we have this is the part where the water chiller is. Here we have the air handling units with fans and with fans. We have like a pump, and we have the cooling towers and the fan. You can be able to use VFDs on these fans and the pumps, so that if it's water, you don't have to pump a lot of water when it is not needed, when the conditions are on the outdoor temperatures are bit low. So you can use the VFD to control the spins of the fans, the spins of the pumps, so that you can be able to reduce the amount of energy being consumed, even when you don't require it, especially when the outdoor air is cool. For example, you want 20 degrees inside, like in a data center, and you find that air is coming at 21. You don't require a lot of water to cool from, say, 21 to 20, compared like if the outdoor air was 25. So you need to be monitoring that. So you can use VFDs, and there are special trainings now for like the cooling towers, where you can do how to handle the cooling towers and the air handling units. So in a nutshell, that is all what we are going to check on that. So on the compressor retrofit, as you have said, if your system is above 150 tons of cooling load, and one ton of refrigerant cooling load is equivalent to around 3.52 kilowatts of thermal, which is being cooled, you don't have to use very big compressors. But once you go above 150 tons of cooling load, you need to employ like screw compressors. And in that case, if you go above like 750, employ centrifugal compressors. So on that case, when you check your load and find that it is within this range, screw compressors are more efficient. At very small units like the outdoor air conditioners, you find it's better used and reciprocated. For the centrifugal units, these are high volume and they are very efficient. They don't deliver a lot of pressure. And what normally happens for you to deliver a lot of pressure, you need to use several of them. These are more like centrifugal fans. So you have to compress the refrigerant in series. But they are very efficient at very high loads. And they are easily controlled by the VFDs. At the same time, for the centrifugal, don't reduce their speed below 20% of the rated speed. They are efficient between above 80% speed. So if you discover that you are going to reduce the load below that, you should either use a screw or use a relatively small centrifugal pump. You can have several. Water chillers come with several compressors. So you can have a system of switching one to another. So as we have seen, it is just a presentation to show you the types of dislocating compressors we have. So these are the types of dislocating compressors. We have like the direct driven ones, and we have the hermetic. The hermetic ones is where the compressor and the motor, all of them are in an enclosed service. These are used for small units, and you don't use them in very big units. The disadvantage of this is that once the compressor is faulty, you cannot easily service them. So they come in small sizes. So these ones use them in small units of water chillers. These are direct driven. They are not automatic, but they are less efficient compared to automatic. So if you are using small units, if you are using small units, you better use automatic than direct driven. Avoid the direct driven as much as possible. We have semi-automatic. If you go to relatively bigger water chillers, smaller than, you can use the semi-automatic. There's a two-stage semi-automatic, one in green, and these are semi-automatic. The difference with semi-automatic and automatic is that the motor is not enclosed in the same place with the compressor, so you can be able to service them. So in this case, motors are serviceable. This one is a two-stage to be able to increase the pressure. For you to do the cooling better, sometimes you require higher pressure. As you have seen in the diagram, TS diagram, the pressures for you to be able to release water within the condenser, for you to be able to release a lot of heat in the condenser, you need higher pressures. So in this case, that's why we normally sometimes employ a two-stage semi-automatic. These are the screw compressors. As you have seen, they are better between 150 and 750 tons, cooling tons. They employ a screw. And the other thing is they can easily be controlled by a VFD because they are not reciprocating. They don't have very many moving parts like the reciprocating compressors. So they are more efficient than the reciprocating. These are the centrifugal. Like this one is a two-stage. You can see it has two turbines, two impellers. And as I've said, it's more of, it operates more like a centrifugal pump or fan. But now it's capable of higher pressure, operating at higher pressure. So you can, if you want higher pressures, you can use a two-stage or a multi-stage. These are two-stage centrifugal. And the good thing with the centrifugal compressors is they handle very big volumes of refrigerants compared to the screw and the reciprocating. And if you move your system from screw to centrifugal, in most cases from experience, you can save up to 20% of the maximum. As you have said, they are very poor when you operate them below 20% of their rated speed. So even if you are using a VFD, make sure that you don't go below 80%. So you can only reduce the speed by 20%. So don't reduce the speeds, because some people go on using a VFD which reduces the speeds up to 50. So you find that you are going below, reducing the speeds below 80% of the rated speeds. It's better to have a system with like two compressors, so that when if the load goes below a situation where you have to reduce the speed below 80, you can switch one off and use the other one. So the savings can go up to 6% or to 9% annually. You can save energies 6 to 9% if you move like from reciprocating or screw compressors to centrifugal compressors. As you have said, in the VFDs, you need to be monitoring the temperatures of the surroundings so that you can be able to use them. You find that most compressors, most chillers don't operate at full load always, because their operations are affected by the requirements of the cooling rooms and the external temperatures. For example, if it's a data center, or if it's a hall, the number of people, if the hall is not full, probably you started with 100 people, and the number of people are reduced to 80, the cooling load will go on reducing. So you have to be, you need to be monitoring the cooling load. Like this one is a graph showing the temperatures of Nairobi in one of the days. That was on 29th April 2021. You find that at around 3, the temperature 2 to 3, the temperatures were 24. But in the morning, at 2 a.m. in the morning, it has reduced to 16 to 17. So this one, if it was like a data center and it's operating the whole night, the whole day at night, you can find during the day the cooling load is higher, and at optimize the cooling load. So you need to employ a VSD so that it can be controlling either the pumps or the compressor and so on. You need to be reducing as long as you work within the 20% we have talked about. This is just a graph showing the outdoor temperatures. You can see at around 4 in the evening, the temperatures are very high compared to 4 a.m. in the morning or at midnight. The temperatures are very low at midnight, but when you go to the morning, 8 a.m. to 12, they go on increasing. So you need to be able to vary. You can see like this one, you measure during an energy audit and you can find the green part is showing the power demand. The power demand is supposed to vary as the temperature is varying. So in such a case, the black part is showing the kilowatts, how the kilowatts is varying as the temperatures are varying. You can see as the temperatures increases, this one increases. So this is an ideal case. This is a good automated case. In other cases, you find that the power demand is like constant, even if the temperatures are low or high. In that cases, during the low temperatures, you are saving less energy. You are wasting a lot of energy. So this is just a photo of a VFD and the connections of VFD. And with that, within 1 year, you can be able to save up to 20% compared to a case where you are running at constant speeds. So we have chilled water reset. As we have seen, if in this air handling units, for example, if the demand for the water temperatures are not very high, you can be able to reset the temperatures up. In the TS diagram, you've seen this line is proportional to the amount of work done by the compressor or the energy consumed by the compressor. In such a case, you can be able to reduce the work done by the compressor by resetting the temperatures very high, by slightly higher than the requirement, probably by 2 degrees or 8 degrees. And in such a case, you can be able to have potential savings of 1 to up to 2%, 1 to 2% of the annual energy savings if you are operating at very low temperatures. So this is one of areas where you can save energy. The other one is the condenser reset. Instead of operating at temperatures which are very high, you can be able to reduce the temperatures. If you monitor the external temperatures, especially if you are using a cooling tower, you can be able to reduce, to reset, so that if the temperatures reach a certain point, water temperature reach a certain point, you can be able to switch off the compressor. And in such a case, you save a lot of energy. This one has to do with the cleaning. You need to have a system to be monitoring. The temperature drops, the coefficient of performance drop, and the pressure drops within the system, especially for air-cooled systems, so that if you reach, for example, a certain point, you can be able to know that's the best time to switch off. Because if you continue running at this point, you'll be wasting a lot of energy. There will be a lot of poor heat transfer between the refrigerant and the water being cooled. So that one is very important. The other one is just to do the change of we talked about expansion valves. Instead of using thermal expansion valves, you can use the electronic valves. This shows how the thermal expansion valves operate. It uses a fluid. It's a volatile fluid, mainly almost similar to the refrigerant. You can see, for you to be able to operate the thermal expansion valve, this fluid needs to expand and push the diaphragm down so that it can allow more refrigerant to the evaporator and to the compressor. So after getting what we call the superheating, the level of superheating after the evaporator, this fluid gets heated and it pushes the diaphragm. So you can see its sensitivity is a bit different compared to that of the electrical systems. You know, an electrical signal moves faster than the expansion because it's more mechanical. So in such a case, if you find they are using, currently you find a situation where they are using the thermal expansion valve, it's better to retrofit it with the electronic expansion valve. And that one you can be able to save around 10 to 14% of the energy annual savings. This is the thermal expansion valve. This is the electronic valve. This is a step motor. So the other one is you have air-cooled compressors. As you said, you can be able to you should be able to switch off. You should be able to switch off some of the fans when the cooling load is not very high. Or you can also have a situation where you replace the fans with the one what we call electronically competent fans. For electrical engineers, you can understand that. So when you go to the market and get the electronically competent valve, this one you can be able now to reduce, to vary the speeds. Because you find most of the times the fans are running at 100%, which is not very good. Sometimes when the load is high, low, you need to reduce the speeds of the fan. Potential savings, 3% to 6%. This is what we call free cooling. You find in a normal situation, the cooling tower is supposed to cool the condenser in the water chiller. And the condenser, then the evaporator cools the chilled water being used in the cooling load. So the circuit originally is supposed to flow, for example, if it's the chilled water is supposed to go to the evaporator, then go back to the cooling. Then the water from the cooling tower is supposed to go to the condenser. But now, if you discover that the external conditions are favorable, they are cold, and this water from the cooling tower can sufficiently cool instead of using the refrigerant now to cool the water for cooling, you can bypass, you can prevent this water from going to the condenser and take it directly to a heat exchanger, then back to the cooling tower, and this water will cool the water in the cooling load and avoid having this water going to the evaporator. In that case, you are going to switch off the compressor completely. I know you're asking why don't we cool using the cooling water from the cooling tower directly. You don't have, it's not good to mix the chilled water and the water from the cooling tower because you can see the cooling tower is open. So this water sometimes gets dirty and we don't want to make the water in the chilled water dirty. So that's why we use a heat exchanger to avoid mixing of the two waters. So in this case, as we said, the compressor is the largest energy consumer. You can be able to switch it off for some times by using direct, what we call free cooling. You can be able to save a lot. That's the condition. The free cooling we are talking about. Also, you can use the outdoor air if you find that the requirements of the indoor air are not very, very far from the outdoor air. Sometimes outdoor air, sometimes it can go up to 18 degrees, and especially in a conference room, you don't require more than 24 degrees. So you can use that one directly. Or in a data center, you don't require more than below 20 degrees, and you have 18 degrees, you can use it directly. Another place, you can be able to replace the cooling tower with a fountain, especially if you're in an area, conference areas. You know, most of the conference areas or hotels are decorated with fountains. Instead of using the cooling tower, you can connect the water from the cooling towers and take it through the fountain, then take it back and use it for condenser cooling. And here you save energy as you enjoy the beautiful environment. This one is very, very effective. Instead of using cooling towers, if you have fountains which run throughout whenever there's a conference, you don't have to employ the cooling towers. And there you save from the cooling tower fans as you enjoy your view. This free energy because cooling towers, the fountains must run to entertain the guests and to keep the guests have a pleasant environment. So you kill two birds with one stone. You enjoy the beauty and you cool the room. Savings, 20 to 50%. The other one is using automatic controls and integrated automatic control system where you can be able to monitor temperatures in the condenser, evaporator, the water, and so on. And they use it now to know which parts to switch off. You know when to switch off the cooling tower fans, when to switch off the cooling tower water, when to switch off the fans, and so on. Integrate all of them. And in such a system, you can be able to save a lot of energy. And some of them, you can even do them remotely. You can use an e-gauge system and use it in a remote way. In the morning, we talked about the real-time monitoring. You can use that one to control. There is one of the systems where you can see as the temperatures were decreasing, the output temperature was decreasing, the power was not changing a lot. Even sometimes it was increasing, even when it's very high. So there's a real case of a band control system which is controlled band. And you can see here, if the controls were good, you could have the power dropping and the temperatures were dropping. As we said, you can also use VFDs in the cooling towers and the pumps and all the auxiliary systems and the air handling units. There are different presentations. You can be trained on cooling towers direct. These are 2-day training, cooling towers and the handling units. So, but VFDs integrated with good control systems, you can be able to save a lot of money. And you enjoy your cool environment. That's the end of the topic. Thank you so much.
Thank you so much, Eustace, for that comprehensive presentation. He has given us more than 11 potential areas to increase energy efficiency in water chillers. And I see you do have questions on the chat. We had one from Cheryl. Cheryl is also part of our YEEP program. She's part of the 10 that are in the first cohort of the Youth in Energy Empowerment Program. Great to see you join in. And her question was on how many tons of cooled air do we draw the line between a small system and a large system when applying the Hamatic compressor? I don't know, Eustace, if that was clear.
Yeah, it's not the amount of air. Okay. But it's the cooling load. Mm-hmm. Cooling load has to do with the amount of heat you have to remove from the service. And this one you can see from it's in the presentation. Before this one. Although the cooling load will also determine the amount of air you have to use in the fan. This one you can do calculations and use the heat transfer equations to know the amount of air you need to put it depending on the temperature conditions. But if you have a cooling load of less than 150, of more than 150, don't use a reciprocating. You should go up to like the screw compressor, for example. If you have more than 500 or 750, go to the centrifugal compressor. I think it's clear.
Yes. Thank you so much, Eustace, for responding to that. You still have 2 more questions. One is from Cyrus, who's asking, on what criteria or strategy do you use to ascertain the need for a compressor retrofit?
Yeah, in fact, it's within this presentation you can see now. As you have said, once you do your energy audit or your design, and you find that the cooling time, the amount of water, the amount of heat you need to remove from the cooled space is above 150, is above 750. You can see now centrifugal fans are very, very good for high cooling loads. For example, more than 70 tons of cooling loads. And the 150 and the screw compressors within the range of 72 to 500.
Thank you so much. I hope that was clear to Cyrus. Thank you for your question. We do have another one from Mubarak, who is asking, for a site with a very high cooling tower, is it advisable to turn off the motor for the air circulation on the power? I hope that was clear.
Could you repeat the question?
For a site with a very high cooling tower, is it possible to turn off the motor for the air circulation on the tower? Maybe he might be referring to the fans on top. I'm not really sure.
You need to monitor the situations and see the amount of, you check the amount of the temperatures of the surroundings and the amount of the temperatures of the place being cooled, of the cooled space, so that you can be able to know when to switch off the fans of the cooling towers and so on. You don't just switch them off automatically. If you find that you can be able to turn off and they do free cooling, that all depends. That's where now we emphasize on the use of controls, so that you can be able to get the integrated control systems where you can be able to measure the temperatures of the surroundings, the temperatures of the place being cooled, the temperatures of the chilled water, the temperature of cooling water, and be able to know what you need to switch off, either the fans of the cooling towers or the pumps, circulating pumps for water, or the compressor. So it's not something you can just sit down and decide that the cooling tower is high, you just switch off. Because that's why I've also seen there is also a training which should be done on the cooling towers, on the design of the cooling towers, so that you can understand how they operate. But all in all, you need a very good control system for your water chillers, so that you can be able to achieve. You can see the control systems, with good control systems, you can be able to achieve up to 20 to 50% of the energy savings.
Thank you. Thank you so much.
It's
I
not
hope
a matter.
Mubarak. Oh, sorry. Okay. Thank you, Eustace, for that. I hope, Mubarak, you have been answered. I'm seeing more questions pouring in. I'll get one from Cindy, who is asking, are there compressors that are not viable to install a VFD? And then lastly, from John Mary, who is asking, have you done remote monitoring of chiller parameters? Which specific parameters do you monitor? Maybe you can answer both of those.
Yeah, reciprocating compressors are not very good for VFDs.
Okay, I think that answers Cindy's question.
And that is why they are used for smaller units. That's why they are used for smaller units. You don't have, they have so many parts and they are normally used for constant spins. At times, if you go on using the spins, they don't work very well. That's why VFDs are good for screw compressors and the centrifugal compressors. The other question was?
The question was, have you done remote monitoring on chiller parameters, and which specific parameters do you monitor?
Yeah, in water chiller parameters, the parameters which are normally monitored is you need to monitor the power consumption at any given time, vis-a-vis the temperatures. Those are mainly the parameters which you measure. The temperatures of the areas being cooled, the temperatures of water, temperatures around the cooling towers, and the temperatures of the refrigerants. So you can do remote monitoring on all those. You find that in water chilling systems, the parameter which we are controlling is to maintain a certain temperature. The other thing you can control and measure the parameter is the humidity, because the humidity also affects the operations of the areas being cooled. If the air is very humid, you need to remove some of the water. So you need to, mainly is the temperature, the humidity, and you can be able to continue monitoring the power consumption of the chiller and its auxiliaries to see how they are matching and see how you can.
Thank you so much. I hope John Mary, you were well answered on that. And a big thank you to Eustace, who has taken us through such a comprehensive presentation today on what are the areas we can improve on our water chiller systems. Thank you so much. Eustace is also a certified trainer for the CEM course. He has done numerous audits, and he's also a certified auditor in Kenya, has a wealth of experience in the industrial application of energy efficiency, and it's been a pleasure to have you here today. And that, ladies and gentlemen, brings me to sort of a conclusion of today's session. I want to thank you everyone for coming. Again, I forgot to mention that there are certificates for attending this webinar stroke training. You will have to attend the first and second day. So looking forward to have you join in tomorrow from 9 a.m. East African time. And speaking of tomorrow, we have 4 more speakers, 4 more topics, all exciting. This session is sort of becoming a melting pot of both knowledge, fun, and networking for energy professionals, energy enthusiasts, and sustainability experts. We have great speakers coming up next tomorrow. We have a topic on energy management. We have another topic on understanding ESCOs. ESCOs stand for energy service companies. We have financing opportunities for energy efficiency projects. If you want to learn how the financing of this projects and programs comes about, we have Trevor Rees on that. And finally, we will have a special session on motors from a trainer from IEPA. Caroline, I see you asking, can someone join in tomorrow? Yes, yes, it will still be, I believe, this link. So looking forward to seeing you all tomorrow. Just to mention that the World Energy Day is in high gear. We want to give a big thank you to UNREA for their partnership and their attendance today, their support. And the next webinar or roundtable that we have will be co-anchored or co-hosted with UNREA, and you're very excited for that. However, looking forward to seeing you all tomorrow. You cannot miss that session. And to John Nganga, who won the activity today, you get a branded mug. So feel free to, I think we will follow up in your details and get that to you. So tomorrow, looking forward to seeing all of you and more. A big thank you to the speakers today, Martin on remote monitoring, Mr. Andersen for the great insights on pre-insulated insulation all the way from Denmark. We had Sylvia Chemongas on compressed air, absolute brilliant on the technologies and how the solutions that we can adopt, and to Eustace Maredi, who has closed it up today. Again, for the presentation, feel free to join the WhatsApp broadcast. We will post the links, the information to the presentation as well. We are recording these sessions. Later on, you will get recordings to this. So it's been an absolute pleasure. You are now free to leave the session. Looking forward to seeing you tomorrow. Mr. Anderson, cannot wait for you to drop down to Kenya later on in the year. It would be exciting to have you in Nairobi for that product training. Looking forward to that. Thank you all.